The Skoda Octavia is built with ruthless precision inside one of Europe's most advanced automotive plants. From automated welding robots to final quality checks down to the millimeter, every step is engineered for performance and reliability. In this video, we go inside the factory floor to see exactly how this popular car is brought to life, from raw steel to showroom ready. The story of the Skoda Octavia begins long before a single bolt is fastened or a robotic arm glides into action. It begins, in fact, with an idea, a blueprint forged in design studios, simulated on computers, and tested in virtual environments by engineers who must balance performance, efficiency, safety, and style. But for our purposes, the journey begins at the factory, where engineering dreams are translated into industrial reality. Welcome to the highly synchronized and precision-driven world of Skoda Octavia production. Every Octavia starts as raw material, high-strength steel coils delivered to the plant by rail or truck, sourced from carefully vetted metallurgical suppliers across Europe. These coils are massive, weighing several tons each, and are stored in a specially climate-controlled steel depot on the factory premises. Before they even reach the production line, each coil is identified with barcodes, batch numbers, and chemical composition data. Technicians conduct tensile strength and thickness tests to ensure the material meets Skoda's exacting standards. Once approved, these steel coils are fed into the blanking line, an automated system that unrolls, flattens, and cuts the steel into large sheet panels. This is no ordinary cutting process. A high-speed hydraulic press slices the sheets using dies that match each specific component, from door frames to hood panels. The accuracy here is down to tenths of a millimeter. Each sheet is then stacked in order, transported by robotic forklifts to the body shop, where one of the most visually captivating segments of production begins. The body shop is a symphony of automation. Over 600 industrial robots, mostly 6-axis KUKA robots, work with millimeter-level accuracy to build what's known as the body in white, the skeletal structure of the Octavia. Here, robotic arms pick up the steel panels and place them into precision jigs. Another set of robots joins them using spot welding. More than 5,000 weld points are applied to a single body shell, each weld carried out in fractions of a second. Sensors within the robots constantly monitor heat, pressure, and positioning to ensure perfect fusion every time. At this point, the vehicle starts to resemble a car, but just barely. The body is incomplete and fragile, still lacking reinforcements, internal frames, and roof components. The roof is attached next, along with the inner structures of the door frames and A-pillars. This structural framing phase is crucial as it determines the vehicle's crashworthiness and rigidity. Skoda uses high-strength boron steel reinforcements in critical areas such as the B-pillar to enhance passenger protection during side impacts. To ensure dimensional accuracy, every fifth body in white is routed to a coordinate measuring cell, an enclosed chamber with laser scanners and mechanical probes that measure thousands of points across the body. Any deviation outside the strict tolerances prompts a quality control response, sometimes resulting in real-time die adjustments or jig calibrations on the production line. With the structural shell now complete, the body is moved via an overhead conveyor system to the next phase, the paint shop. But before any paint can be applied, the shell undergoes one of the most chemically intensive processes in the factory, the pre-treatment line. Here, the body is dipped into a series of 12 to 14 baths, starting with alkaline cleaners that strip oils and residues from the welding process, followed by zinc phosphate baths that apply an anti-corrosion layer at the molecular level. This immersion is done using a massive rotodip system, which rotates the entire body in white 360 degrees in giant tanks, ensuring every surface, cavity, and seam is fully treated. After rinsing and drying, the shell enters the electro-coating tank, where an electrical current is passed through a special primer solution. The car body acts as a cathode, attracting the primer particles, which adhere uniformly even inside tiny crevices. This electrophoretic coating forms the first of several protective paint layers. From here, the body moves into sealed spray booths where automated sprayers apply multiple coats of paint, typically a base coat for color and a clear coat for gloss and UV protection. The environment inside these booths is tightly controlled. Temperature, humidity, and air pressure are constantly monitored to prevent dust intrusion or paint imperfections. Any deviation can lead to paint defects like orange peel or fish eyes, which are not tolerated on the line. Once painted, the shell is moved into a high-temperature oven or curing oven, where it is baked at around 150 to 180 degrees Celsius for up to 30 minutes. This curing process chemically bonds the paint to the metal, hardening it into a resilient shell. After cooling, a small team of human inspectors examines each body under specialized lighting tunnels, checking for the slightest flaws in gloss, color uniformity, or texture. Any imperfection, no matter how small, is flagged, buffed, or resprayed. Next, the painted shell enters what is known as the trim and final assembly area, arguably the most complex and human-intensive part of the production line. It's here that the skeletal shell of the Octavia transforms into a functional vehicle. The doors are removed temporarily and sent down a separate subline for internal fitting. This allows easier access for workers and robotic systems to install key internal components like dashboards, wiring harnesses, HVAC units, and center consoles. The main body, now called the marriage body, proceeds on a conveyor to the cockpit station. Here, large sub-assemblies, pre-assembled in adjacent areas of the factory, are carefully fitted into place. The dashboard unit, including instrument clusters, infotainment systems, and climate controls, is mounted in one seamless motion using a robotic assist arm designed to handle sensitive electronic modules without damaging connectors or wiring. Wiring harnesses, which serve as the car's nervous system, are routed throughout the body with meticulous care. These harnesses contain dozens of bundled cables, each color-coded and tagged for correct routing to lights, sensors, powertrains, and control modules. Workers follow digital torque instructions via handheld screwdrivers with built-in sensors that alert them to any over or under tightening of critical fasteners. Every step is logged digitally to ensure traceability down to the individual component level. At this stage, the car receives its interior features: carpeting, seats, airbags, and insulation. The seats themselves arrive as complete modules, built in a just-in-time fashion by nearby suppliers and delivered to the line by autonomous mobile robots. Each seat is barcoded and matched to the specific configuration of the car: cloth or leather, heated or ventilated, manual or power adjusted, and installed in one swift but carefully measured motion. As the Skoda Octavia's skeletal structure is now fully formed, painted, and partially assembled with its interior trim and wiring infrastructure in place, the process turns toward one of the most crucial phases of all: the marriage of the car body with its drivetrain and chassis. This stage is where the Octavia transitions from a lifeless shell into a machine capable of movement, energy, and direction. The drivetrain, consisting of the engine, transmission, front and rear axles, and various suspension components, is assembled separately in a highly organized and synchronized subline known as the powertrain line. This area operates like a standalone microfactory, complete with its own logistics network, inspection checkpoints, and robotic assistance. Engines are delivered from Skoda's engine plant, typically either turbocharged TSI petrol or TDI diesel configurations, though plug-in hybrid variants also have their own specialized integration procedures. These engines arrive as complete units, fully tested, barcoded, and preloaded with essential fluids. Upon arrival, the engines are mounted onto steel cradles, also called front-end modules or subframes, where additional components such as radiators, electric fans, intercoolers, and sometimes the front suspension wishbones are attached. At the same time, transmission units, whether manual or DSG dual-clutch gearboxes, are bolted directly onto the engine block. Robotic torque arms perform these operations with absolute consistency, while sensors record every bolt's torque and angle to ensure mechanical integrity. Meanwhile, on the chassis line, rear axle assemblies are prepared in parallel. For models with multi-link rear suspension, this step includes fitting the control arms, coil springs or dampers, rear disc brakes, and sometimes independent electric motors for all-wheel drive variants. These modules are mounted onto jigs and temporarily stored until they're summoned into position by the main assembly control system, which tracks each vehicle's configuration in real time. Now comes the literal marriage of body and chassis, a highly choreographed operation involving synchronized lifts, conveyor positioning, and robotic alignments. The body of the Octavia, suspended overhead by a guided hoist system, is lowered onto the rolling chassis below with astonishing precision. This alignment must match dozens of mounting points simultaneously: engine mounts, subframe bolts, suspension towers, and driveshaft couplings. The hoist slows its descent incrementally, guided by both optical sensors and laser alignment systems. Once body and chassis are joined, a team of skilled technicians manually fastens the major anchor points, assisted by torque-limiting pneumatic tools. These connections are critical as they determine the vehicle's handling, NVH characteristics, and structural behavior under stress. Each bolt's completion is digitally recorded and verified in the manufacturing execution system, creating a digital fingerprint for the vehicle. Following this milestone, the car begins to resemble a finished vehicle. It now moves under its own chassis wheels onto the next phase: wheel mounting and fluid filling. Tires and wheels are mounted using automated stations that retrieve the correct size and style based on the car's build sheet. Steel wheels, alloys, summer or winter tires, depending on market and order. Robotic arms guide the wheels onto the hubs, while nut runners fasten them in a star pattern to ensure balanced torque distribution. With wheels fitted, the vehicle enters a sophisticated fluid station where all operating fluids are automatically filled. These include engine oil, brake fluid, coolant, transmission fluid, and refrigerant for the air conditioning system. Nozzles are inserted into designated ports, and the exact volume is dispensed under pressure control to ensure no air pockets or underfilling. The brake lines and fuel system are pressure tested during this stage for leaks, and any deviation triggers a diagnostic halt. Electrical systems are now connected and initialized. The vehicle receives its battery, alternator links, and fuse box connections. Diagnostic tools plug into the onboard OBD port to initialize and verify all electronic control units, engine ECU, body control module, infotainment systems, safety sensors, and more. This moment is often referred to as the car's first heartbeat, the first time it powers up electronically and is capable of communication and self-diagnosis. It's also now that the vehicle's doors, which were sent down a parallel sub-assembly line earlier, are reattached. During their absence, each door was fitted with inner paneling, window regulators, speakers, insulation, locking mechanisms, and trim. Robotic arms lift the doors back into position and attach them using high-torque fasteners. Workers verify door alignment, shut lines, and hinge tension to ensure smooth operation and flush fitting. Window calibration tools are also used to check automatic up-down functions, pinch protection, and sealing. At this point, the Octavia proceeds to the dynamic calibration area, Although the car is not yet ready for the open road, it undergoes an initial set of tests to calibrate sensors, align components, and validate subsystem communication. A wheel alignment station uses high-precision optical cameras to adjust toe, camber, and caster angles according to factory specs. Headlights are calibrated in beam testing bays, where optical targets are used to adjust the throw, height, and spread of the light, especially critical for models equipped with adaptive matrix LED systems. Next, the car undergoes brake and suspension testing on a rolling test rig. The vehicle is driven onto a large multi-roller dynamometer where the wheels spin under resistance. During this process, technicians activate the braking system, monitor deceleration curves, and verify that ABS and ESC systems respond as programmed. The suspension is also checked for compliance and noise using vertical shakers that simulate uneven road surfaces. Any creaking, excessive travel, or rattling results in an immediate pull for inspection. A particularly fascinating step follows: the water leak test chamber. Every single Octavia is driven into a sealed tunnel where high-pressure water jets blast the entire vehicle from multiple angles. The test simulates intense rain, car washes, and flood-like conditions. Sensors placed inside the cabin, along with absorbent test materials, detect even the slightest intrusion of moisture. This ensures the integrity of window seals, door gaskets, light assemblies, and sunroof drains. Emerging dry and intact from the water test, the Octavia proceeds to the finishing line, where final interior fittings and cosmetic elements are installed. This includes steering wheels, emblems, gear shift knobs, floor mats, decorative trims, and external badges. Infotainment software is uploaded or updated over a secure network, often using factory-wide Wi-Fi protocols. The vehicle's VIN is permanently etched into structural components and logged in the company's global tracking system. One of the last human-centric inspection areas is the quality audit tunnel. Here, specially trained inspectors perform a 360-degree check under high-intensity lighting to detect any aesthetic flaws, paint imperfections, trim misalignments, stitching errors, or even tiny scratches on window glass. They also run functional checks, including horn operation, screen responsiveness, ventilation airflow, mirror adjustability, and seat motor function. Every button, switch, and knob must perform flawlessly. Before the vehicle can be declared finished, it must complete one more critical phase, the road test loop. A selected percentage of vehicles from each production batch, typically 1 in every 20, are driven on a dedicated outdoor or indoor track. This track simulates real-world driving conditions: cobblestones, sharp turns, acceleration zones, and braking areas. Skilled test drivers listen for unusual sounds, assess steering response, and monitor transmission behavior. Advanced onboard diagnostics log performance metrics throughout the test drive. Once approved, the Octavia returns to the factory's logistics area, where it undergoes its final configuration. Region-specific features such as language settings, radio frequencies, emissions labeling, and immobilizer coding are finalized. Vehicles destined for specific markets, Germany, UK, Scandinavia, or overseas, are grouped together and scheduled for shipment. Once a Skoda Octavia rolls off the production line, fully assembled, tested, and approved, it doesn't simply sit idle awaiting its new owner. What follows is an equally critical, meticulously orchestrated process that transitions the finished vehicle from factory floor to dealership showroom. This final stretch of the production journey may not involve welding robots or paint curing ovens, but it requires an intricate ballet of logistics, digital systems, quality assurance, and environmental controls to ensure that each car arrives in pristine condition, configured perfectly for its destination market. The first step begins at the vehicle dispatch yard, a massive, secure expanse typically located adjacent to the main factory grounds. This area operates like an open-air inventory matrix. Rows of finished Octavias, arranged by drivetrain type, paint color, market region, and model variant, are lined up with absolute geometric precision. Each vehicle's location is tagged via RFID or barcode systems and updated in real time into Skoda's global logistics management platform. The platform tracks not only the physical location of each vehicle, but also its production status, destination, and shipping schedule. Before any vehicle can be released for shipment, it undergoes a final series of checks in the pre-delivery quality assurance zone. This area acts as a last filter to catch any deviations that might have occurred during the assembly or post-test handling stages. Workers inspect tire pressure, verify that protective films are applied correctly to scratch-prone areas like door edges, mirrors, and bumpers, and confirm that all software systems are up to date. Vehicles fitted with GPS or SIM-based connectivity receive final activation or regional adjustments depending on local telecom regulations and data privacy laws. Another important step here is the market-specific homologation procedure. While the Octavia platform is globally standardized, various regulatory requirements differ from country to country. Vehicles destined for the UK, for example, require right-hand drive steering, headlight angle adjustment, and specific compliance markings on safety stickers and child lock labels. Similarly, North African or Middle Eastern versions often come with enhanced cooling systems, battery conditioning for high-temperature zones, and multilingual interfaces for infotainment and vehicle manuals. Each car is thus finalized for its end-user region with absolute attention to detail. Once cleared for dispatch, the logistical journey begins. Cars are loaded either onto multi-deck car carrier trucks or specialized automotive freight trains, depending on destination. For continental European markets, rail transport is the norm, as it allows for the movement of dozens of vehicles at once with low emissions and high security. These trains are purpose-built with adjustable platforms to accommodate various vehicle heights and lengths, and the loading process itself is conducted using hydraulic ramps and wheel guides to prevent any possibility of contact or scratching. Vehicles are secured in place using soft straps over the tires, never hard points on the bodywork, to avoid any damage. Drivers and loaders follow strict speed limits and turning angles during the loading process, and each movement is logged electronically with timestamps and operator ID for full traceability. The outbound transport system functions on just-in-time scheduling. Transport is aligned tightly with dealership stocking cycles and customer orders, meaning that most Octavias are delivered to retail networks within days of completion. For overseas markets such as Australia, Japan, or South Africa, the vehicles are routed to maritime logistics hubs, most notably in German ports like Bremerhaven or Hamburg. Here, cars are parked in holding zones until their shipping vessel arrives. Before boarding the ships, known as roll-on, roll-off, or ro-ro vessels, each Octavia undergoes a salt spray protective procedure, which includes the application of temporary wax coatings on vulnerable areas like undercarriages and wheel wells. Mirrors are often folded in or protected with soft plastic covers, and battery terminals may be disconnected during long journeys to preserve charge levels. Ro-ro vessels are essentially floating parking garages. Cars are driven into the lower decks via wide ramps, then secured in rows using floor hooks and wheel chocks. Temperature and humidity are monitored throughout the voyage, and any incident or deviation is logged and communicated back to Skoda's central logistics team. These teams use real-time satellite tracking and predictive ETA algorithms to coordinate arrival times, customs clearance, and inland transport schedules for each destination port. Upon arrival in the destination country, The vehicles are offloaded and temporarily stored at an importer's distribution center, known in industry terms as a vehicle processing center. These centers act as a final staging ground before cars are delivered to dealerships. Here, the Octavia undergoes another series of inspections and market preparations. Protective films are removed, final cleaning is done, and country-specific accessories like license plate frames, floor mats, or regional documentation packets are added. The vehicle's onboard software may receive updates or localizations, such as voice command packs in specific dialects or region-locked infotainment functions like radio bands or mapping data. Any vehicle requiring customization at the VPC, such as fleet vehicles with special paint schemes, decals, or upfitting, undergoes a rapid accessory installation. This is also the point where final compliance documents are printed and affixed, including emission certification, tire labeling, and VIN stickers that align with the country's Department of Transportation or equivalent authority. Once cleared, the car is loaded onto local transport carriers, usually single or double-deck trucks designed for short-haul deliveries to regional dealers. These trucks operate on a tightly managed schedule coordinated between the manufacturer, logistics provider, and the dealership's sales team. Dealerships receive advance notice of incoming units, complete with full configuration specs, production history, and electronic handover documentation. This allows showroom staff to prepare for vehicle delivery, organize customer paperwork, and schedule test drives or handovers for buyers who've pre-ordered their Octavia. Upon arrival at the dealership, the vehicle enters the final stretch of its preparation lifecycle. Dealership technicians perform what's known as the pre-delivery inspection. This process involves checking battery voltage, verifying tire pressures again, updating software to the latest firmware release, and confirming that all onboard systems are functioning correctly. The technician also syncs the vehicle's telematics systems with the customer's profile if it's a connected vehicle, ensuring seamless onboarding for the driver. Exterior cleanliness and presentation are paramount here. The vehicle is washed, dried, and polished. Any interior protection, seat covers, plastic film on displays, is removed carefully to preserve the new car sensation. The vehicle's infotainment system is often demoed for the customer in advance, showing off features like wireless Apple CarPlay or Android Auto, adaptive cruise control settings, or integrated Skoda Connect services. The car is now ready for customer delivery. But beyond just logistics, the entire system that supports the delivery of the Skoda Octavia is also an achievement in manufacturing scalability and digital synchronization. Every car, from the moment a production slot is assigned to the instant its keys are handed over to a new owner, is tracked, scheduled, configured, and quality controlled to within an inch of perfection. Even after the sale, onboard diagnostic tools and telematics systems report service needs, software, update availability, and potential issues, creating a lifecycle loop that feeds directly back to Skoda's engineering and production planning teams. For example, if a particular batch of Octavias reports slightly increased wear in rear suspension bushings under certain climate conditions, engineers can trace the data back to specific suppliers, production dates, and even sub-batch quality readings. This creates a feedback loop that not only improves future vehicles, but enhances predictive maintenance and customer satisfaction. Behind the gleaming bodywork, smooth ride, and modern technology of each Skoda Octavia lies a staggering network of systems, people, machinery, and logistical engineering. From zinc-coated steel coils and precision robotic welds to cross-continental transport vessels and digital dealership diagnostics, the Octavia isn't just built, it's orchestrated in harmony with thousands of moving parts and processes, each time to perfection. And all of it, every robot weld, Every bolt tightened to exact Newton meters, every barcode scanned, is done not simply to build a car, but to deliver an experience, one of reliability, safety, performance, and pride of ownership. That's the promise that begins in the factory and ends in the driver's seat. To truly understand the scale and precision behind Skoda Octavia production, one must look beyond the factory floor and consider the intricate network of component suppliers and upstream systems that feed into the assembly line. For every car that takes shape in the factory, hundreds of specialized parts must arrive on time, in the right sequence, and in the correct specification. This vast, synchronized network is known in the automotive world as the supply chain, and in the case of Skoda, it's a marvel of real-time coordination, supplier partnerships, and just-in-time logistics. Each Skoda Octavia comprises over 6,000 individual parts. These components range from large visible systems like wheels, windshields, and headlights to invisible but critical parts like engine sensors, fuel injection regulators, gasket seals, and control module chips. Roughly 65 to 70% of these parts are manufactured by Tier 1 suppliers, companies that deliver fully assembled modules or high-value systems directly to the car maker. The remaining proportion includes Tier 2 and Tier 3 suppliers that deliver subcomponents to the Tier 1s for further integration. Consider the dashboard module, for example. This is not simply a plastic structure. It includes integrated climate ducts, wiring harness brackets, infotainment mounts, and sometimes even embedded ambient lighting strips. A supplier like Faurecia or Lear might produce this complete dashboard unit off-site at a satellite plant located within 50 to 100 kilometers of the main Skoda facility. Their production runs in parallel with Skoda's own line, synchronized by shared production schedules and EDI systems. These EDI platforms are the backbone of modern automotive manufacturing. Through these systems, Skoda communicates real-time build orders to each supplier based on customer demand, line performance, and inventory levels. If a sudden influx of Octavia orders requires an uptick in 1.5 TSI engines with manual gearboxes, Skoda's system sends this data down the chain, prompting engine module suppliers to adjust output and delivery timing. This just-in-time model reduces storage needs and waste, but it requires near-perfect execution and reliability across the board. Every part entering the Skoda plant is tagged with unique barcodes or RFID labels. Upon arrival at the factory gates, incoming deliveries are scanned, inspected, and logged. The parts are then sent either directly to the line or stored in high-efficiency automated warehouses called ASRS. These towering computer-controlled storage units use robotic cranes and conveyors to quickly retrieve parts as needed, feeding them into the production line in a seamless, real-time flow. But the supply chain is about more than just timing. Quality control is paramount. Each supplier is required to adhere to Skoda's supplier quality standards, which are monitored through periodic audits, statistical process control data, and end-of-line checks. If a batch of components falls outside tolerance, say windshield washer motors with torque output below spec, they are quarantined and the supplier is notified immediately via automated quality feedback portals. This attention to quality also extends to the software components in modern Octavias. Today's cars are as much digital machines as they are mechanical ones. Software for ECU modules, infotainment units, ADAS, and telematics is developed months in advance and tested in closed-loop systems before being validated for installation. These software packages are pushed to the factory through secure networks and flashed onto control modules during vehicle assembly. Security is paramount here, and all software updates are cryptographically signed to prevent tampering or breaches. Now, let's turn to automation, one of the defining features of modern Skoda production. While humans remain central to the assembly process, particularly in tasks requiring judgment, dexterity, and customization, the factory itself is driven by an intricate web of automated systems. Conveyors, robots, AGVs, and digital twins all work in harmony to keep the line moving with minimal interruption. AGVs are one of the most visually striking elements of this system. These robotic delivery vehicles navigate factory floors autonomously, delivering everything from suspension arms to steering wheels to the correct workstation, guided by a combination of magnetic tracks and onboard LiDAR systems. Each AGV is linked to the MES and can reroute itself based on real-time production changes. For example, if a specific model is delayed in paint, the AGV carrying its corresponding seat set can be redirected to a holding buffer without human intervention. Overhead, conveyor systems run in tandem with the floor-level automation. These ceiling-mounted rail systems transport car bodies from one section of the plant to another, lifting and rotating them to allow ergonomic access for workers and robots. In some areas, these conveyors also include turntables and elevator modules that adjust height and orientation based on the assembly phase. This ensures not only productivity, but also worker safety and comfort. One of the most powerful tools in Skoda's production arsenal is its use of digital twin technology. Every car moving down the line has a virtual counterpart in the cloud, an exact digital representation of its configuration, assembly status, component origins, and inspection results. This digital twin is updated in real time and can be accessed by plant managers, quality engineers, and logistics coordinators. If an issue arises, say a misalignment detected in a body panel, the digital twin records the anomaly, associates it with the production station and shift in which it occurred, and notifies the relevant teams for root cause analysis. Digital twins are also critical in training and simulations. Before a new variant of the Octavia is introduced, engineers and planners can simulate the entire build process, testing new tools, layouts, or work sequences in virtual space. This allows Skoda to implement changes quickly with minimal disruption to ongoing production. It also reduces the number of physical prototypes needed for process validation, saving both time and cost. While robotics handle many of the repetitive and high-precision tasks, human workers remain essential, particularly in the trim and final zones where interiors, wiring, and complex assemblies come together. To assist them, Skoda deploys a suite of ergonomic tools and digital aids. Torque-controlled power tools connected to overhead reels allow workers to fasten components without strain. Visual instructions and torque values are displayed on smart monitors at each station, updating in real time based on the vehicle moving down the line. Smart gloves and wearable scanners are also used, allowing technicians to confirm part identity and orientation before installation. Each human operator is trained extensively, with many going through weeks of classroom instruction, simulator-based practice, and shadowing experienced colleagues. Certification is required for each workstation, and retraining is done periodically or whenever a new process is introduced. Safety is integral to all of this. Sensors monitor motion zones to prevent collisions. Alarms trigger if tools deviate from preset thresholds, and workspaces are equipped with height-adjustable platforms and cushioned mats to reduce fatigue. Behind all of this is a powerful production planning system. Long before a single Octavia reaches the line, planners model capacity forecasts, supplier lead times, labor scheduling, and shift rotation schemes using AI-based algorithms. These tools factor in order backlogs, regional model demand, holidays, and even weather patterns that might affect logistics. If a snowstorm is predicted in a key transport corridor, the system automatically recommends schedule shifts or alternate distribution routes to avoid disruption. Energy efficiency is another area where Skoda has made major strides. The factory is equipped with heat recovery systems, solar arrays on the roof, rainwater harvesting systems, and intelligent lighting that adjusts based on occupancy and daylight levels. Paint shops, traditionally among the highest energy consumers in automotive production, are now equipped with dry scrubber technology and thermal recirculation to minimize waste. Even conveyor motors are equipped with regenerative braking systems to recover energy during deceleration phases. Sustainability doesn't stop at the factory gates. Suppliers are audited not just for quality and delivery performance, but also for environmental and social responsibility. Skoda enforces compliance with ISO 14001 standards across its tiered supply network and encourages local sourcing where feasible. Packaging materials are standardized and reusable, and component shipments are consolidated wherever possible to reduce carbon footprint. To further appreciate the engineering and manufacturing depth of the Skoda Octavia, one must explore the extensive customization capabilities and flexible production architecture that allows this single vehicle line to cater to a wide global audience. The Octavia is not a one-size-fits-all car. It is offered in multiple body styles, powertrain options, interior trims, and equipment levels, all of which are supported by a sophisticated manufacturing system built upon modularity, scalability, and lean manufacturing principles. At the heart of Skoda's flexibility lies the Volkswagen Group's Modulare Querbaukasten, or MQB platform. Introduced to harmonize development across different vehicle classes, MQB is a transverse modular toolkit that allows shared use of components such as engines, transmissions, suspension geometry, and electrical architectures across various models. In the case of the Octavia, it shares its underlying platform with vehicles like the Volkswagen Golf, Seat Leon, and Audi A3. This commonality enables Skoda to produce multiple variants of the Octavia: sedan, wagon, hybrid, gas-powered, diesel, and even mild hybrid versions, without requiring completely separate production lines. Rather than viewing the Octavia as a single product, Skoda treats it as a configurable structure within a tightly coordinated production matrix. When a customer places an order, either through a dealership or an online configurator, that order flows into Skoda's central planning database, where it's translated into a digital build sheet. This document specifies every aspect of the vehicle: engine type, transmission, drive layout, infotainment system, upholstery, wheel design, active safety packages, regional adaptations, emission certifications, and even factory-installed accessories like roof bars or tow hitches. Each of these variables is governed by a set of compatibility rules managed by Skoda's product configuration logic. For example, a high-output diesel engine may not be available with the base trim level due to cooling and chassis constraints. Similarly, specific radar-based safety systems might only be installable on variants with a certain type of front bumper or interior digital cockpit. These conditional dependencies are resolved automatically by the back-end systems, which check for engineering feasibility before locking in the order. Once an order is confirmed, it is slotted into a dynamic production schedule that balances model mix, resource availability, and factory efficiency. Importantly, Skoda does not build vehicles in strict order of sales. Rather, it builds them in an optimized sequence that minimizes setup time, balances labor load, and stabilizes part consumption rates. This method, sometimes referred to as level scheduling, is one of the cornerstones of lean manufacturing. It prevents bottlenecks, allows for better supplier coordination, and reduces the amount of time the car spends in the factory. As a result, two cars traveling down the line might look identical from the outside, but be completely different beneath the surface. One a plug-in hybrid with heated rear seats and check navigation. The other, a base model petrol version for export to North Africa. To manage this complexity, each station along the line reads the vehicle's digital build sheet in real time. Screens above the workstations display step-by-step instructions tailored to that exact configuration, while pick-by-light systems guide workers to the correct bins and component trays. This is particularly important during interior assembly, where the number of possible permutations is vast. From dashboard colors and decorative inserts to seat foam densities and steering wheel types, the interior is one of the most customized parts of the car. Workers receive seating units pre-tagged with RFID matched to the car via an automated delivery system. The steering column, infotainment interface, gear selector, and even pedal assemblies are chosen based on each vehicle's order code. Robotic torque arms are reprogrammed automatically to apply different fastening sequences depending on the equipment level and trim variant. The same modular logic applies to the powertrain station. The MQB platform allows various engine and transmission combinations to be mounted onto the same chassis architecture. Whether a car is receiving a 1.0 TSI petrol engine or a 2.0 TDI diesel with all-wheel drive and DSG transmission, the mounting points, wiring harness routing, and cooling integration follow standardized paths. The robotic systems that perform engine marriage operations adjust in real time based on the digital instruction set received for each car. Emissions compliance is another area where the system's flexibility shines. Vehicles bound for different regions must meet different regulatory standards: Euro 6D in Europe, Bharat, Stage 6 in India, or Tier 3 in the United States. This affects more than just engine calibration. It can influence the selection of catalytic converters, onboard diagnostics, fuel vapor recovery systems, and exhaust layout. The assembly line is capable of dynamically adapting these configurations during the final powertrain integration phase. Emission sensors are tested and validated before the car moves to final quality check, ensuring full compliance before leaving the plant. This high degree of customization has forced Skoda to develop exceptionally refined in-house logistics and traceability tools. Every part, from a bolt in the seat frame to the circuit board inside a camera module, is traceable back to its source, down to the supplier batch and timestamp. If a defect is later discovered in a specific part, such as a faulty capacitor in an ABS module, Skoda's quality team can instantly identify all affected vehicles, notify dealers, and even pre-position replacement parts for proactive service campaigns. But the complexity doesn't end at physical hardware. Modern Octavias are packed with software-controlled systems: lane assist, adaptive cruise control, parking sensors, matrix LED lighting, automatic emergency braking, and connected infotainment platforms. Each of these systems has embedded firmware that must be updated and calibrated before delivery. In some cases, over-the-air updates can be performed after the car is sold, but many functions still require factory-level activation and testing. To streamline this, Skoda uses central configuration tools that compile a software bill of materials for each vehicle. As the car moves through assembly, each electronic control unit is flashed with its specific firmware version, encrypted and authenticated via secure keys. A final system integration test validates that all ECUs are communicating properly, known as a KN bus verification, and that diagnostics are error-free. If any faults are detected, the car is automatically diverted to a diagnostics bay for further analysis. Such granularity and flexibility would not be possible without an empowered and highly skilled workforce. Skoda invests heavily in training and upskilling its production teams. Every new employee undergoes a rigorous onboarding program that includes mechanical skills, safety procedures, quality assurance basics, and an introduction to the Skoda production system. For specialized roles like engine mounting, suspension calibration, or electrical integration, additional certifications are required. These are renewed annually to ensure procedural consistency and up-to-date knowledge. Continuous improvement, or Kaizen, is another foundational principle. Employees are encouraged to identify inefficiencies or risks and propose improvements through structured feedback channels. Many line-side innovations, such as tool redesigns, ergonomic adjustments, or improved material handling flows, originate from shop floor operators. Each suggestion is reviewed by a dedicated process engineering team and, if feasible, rapidly prototyped and implemented. Even the work environment itself is engineered for performance and health. Skoda's factories are designed with natural light corridors, clean air circulation systems, sound dampening materials, and climate-controlled zones. Workstations are height adjustable, parts bins are positioned within optimal reach distances, and ambient noise levels are monitored to prevent long-term exposure risks. In areas with repetitive motion, exoskeletons or assistive lifting arms are provided to reduce physical strain. Skoda's ability to build thousands of highly individualized vehicles per week is not simply a triumph of machinery. It's a reflection of disciplined process design, human system integration, and scalable modularity. Whether assembling a performance-oriented Octavia RS with sport suspension and dual exhaust, or a fuel-sipping mild hybrid for city commuting, the line adapts fluidly. Every Octavia is not just a copy of the last. It is a response to a unique customer need, tailored precisely and efficiently thanks to the architecture of customization that Skoda has refined over decades. The creation of a Volkswagen Golf, one of the most iconic hatchbacks in automotive history, begins long before any metal is stamped or bolts are torqued. To truly appreciate the intricacy and precision of its manufacturing, we need to understand that this process represents the culmination of decades of engineering refinement, logistical coordination, and factory automation. It is not merely the assembly of components, but the orchestration of thousands of interdependent systems working in harmony, each with a dedicated role in transforming raw materials into a vehicle ready to roll off the line and onto the world's roads. The process begins at the heart of the operation, the Volkswagen manufacturing plant. One of the most famous Golf production facilities is located in Wolfsburg, Germany, where massive halls the size of several football fields stretch out in every direction. The atmosphere inside is clinical, controlled, and buzzing with quiet energy. Contrary to what one might expect, these spaces are not chaotic or deafening. They are meticulously organized, highly automated environments where human expertise collaborates with robotic precision to produce each vehicle to exacting standards. The first chapter in the physical birth of a Golf begins with the fabrication of the car's body shell. This process is commonly referred to as body in white, and it involves the welding and joining of raw sheet metal components that form the structural skeleton of the vehicle. These metal sheets typically arrive at the factory in pre-cut and coiled form, having been sourced from steel and aluminum suppliers who produce automotive-grade alloys with specific mechanical properties such as tensile strength, corrosion resistance, and energy absorption. Volkswagen has stringent quality controls on these materials, inspecting incoming shipments with laser scanners, chemical analysis equipment, and tensile testing machines to ensure that every roll meets the necessary specifications for forming and crash safety. Once approved, the metal sheets are uncoiled and fed into gigantic press machines, many stories tall, in what is known as the stamping area. These presses are a marvel in themselves, each capable of exerting thousands of tons of pressure. Using a combination of progressive and transfer dies, massive steel molds engineered to exact tolerances, these machines punch, bend, and form individual components like doors, hoods, roofs, floor panels, and side frames. Each die can weigh up to 40 tons and requires highly precise installation. The press line operates with the rhythmic certainty of a mechanical heartbeat, with each panel ejected onto a conveyor system that ferries it toward the next phase of production. From here, the stamped panels enter the body shop. This area is perhaps the most robot-dominated zone of the entire plant. Hundreds of robotic arms, painted in Volkswagen's signature orange or yellow, perform an intricately choreographed ballet of spot welding, laser welding, and riveting. These robots are guided by 3D coordinate programming and vision systems that allow them to make microscopic adjustments in real time. Their work is critical, as the dimensional accuracy of the welded body frame dictates how well later components, like the drivetrain and interior modules, will fit. The vehicle begins to take shape as floor panels are married with the side structures. Roofs are laser welded into place, and reinforcement beams are added to strengthen key impact zones. The welding robots are just one part of this highly automated process. In certain sections, human operators are still essential, particularly for tasks requiring dexterity, visual inspection, or adaptation to model variants. At these stations, workers equipped with pneumatic tools and ergonomic lifts work alongside the robots to install structural reinforcements, apply bonding agents, or verify alignment with laser-calibrated measurement systems. Every completed body shell is then run through a geometric measurement tunnel, where a series of cameras and lasers scan the surface down to the sub-millimeter level, ensuring that each vehicle conforms precisely to Volkswagen's quality blueprint. Once the body-in-white structure is completed and quality verified, the next transformative phase begins, the painting process. But before any color is applied, the raw metal body must be prepared to resist corrosion and adhere properly to the paint layers. The shell first passes through a cleaning and pre-treatment bath, typically involving a series of immersion tanks where it is cleaned of oils, particulates, and oxidation. This is followed by a process known as cathodic electrocoating, or e-coating. Here, the entire body is submerged in an electrically charged bath containing anti-corrosion primer particles. A low voltage current causes the primer to be drawn onto every metal surface, even inside closed box sections, providing complete and uniform protection. After e-coating, the body is dried in a curing oven and then transferred into the paint booths. These clean rooms are maintained at highly controlled temperature, humidity, and dust levels. The next steps involve the application of a primer layer, base coat, and clear coat, each sprayed using high-precision rotary atomizers. Robots again take the lead here, moving with fluid, sweeping motions to ensure a uniform paint film. Each coat is flash-dried between applications, and the final clear coat is cured in another high-temperature oven. Color accuracy and surface quality are assessed by specially trained technicians, often under special light tunnels that reveal even the most subtle defects or inconsistencies in the paint finish. With the painted body now cooled and cured, it proceeds to the marriage with the mechanical underpinnings, the powertrain, suspension, and chassis components. This phase marks the beginning of the general assembly process, which is one of the most logistically complex and human-involved areas of the plant. The painted body is mounted onto a continuously moving conveyor line known as the assembly line or production line, and begins its journey through a sequence of stations, each responsible for a specific set of tasks. One of the first major milestones on this line is the marriage station. Here, the body shell is carefully lowered onto a pre-assembled chassis, which includes the engine, transmission, front and rear axles, brake lines, fuel system, and other underbody modules. This process is performed using automated lifting gantries equipped with positioning sensors and torque control systems, ensuring that every bolt, mount, and fastener is attached with the correct torque specification. At this stage, precision is paramount. The alignment of engine mounts, suspension geometry, and drivetrain clearances are all verified, using computer-aided fixtures and sensor feedback systems. As the car progresses down the line, workers and robots alternate in adding increasingly complex subsystems. Wiring harnesses, which have been pre-assembled in a separate part of the plant, are routed through the vehicle's interior and connected to key modules. These harnesses are essentially the vehicle's nervous system, containing hundreds of electrical wires that link sensors, control units, lighting, safety systems, and infotainment components. Routing these bundles accurately and securing them with clips, grommets, and tie wraps is both an art and a science, requiring a balance between accessibility, safety, and electromagnetic shielding. Following this, the interior components begin to enter the scene. Dashboards, HVAC units, center consoles, and infotainment displays are installed using guided insertion tools and laser alignment rigs. The seats, which are often built in a just-in-time fashion by a nearby supplier, are delivered directly to the line and bolted in place using high-torque pneumatic tools. Throughout this process, every module is scanned with a barcode reader to ensure traceability. This level of digital tracking allows Volkswagen to log the exact batch, supplier, and assembly timestamp for every major component, creating a complete digital twin of the vehicle's production history. By this point, the Golf has become instantly recognizable, with its iconic silhouette now cloaked in paint and outfitted with much of its interior. However, many critical systems have yet to be tested or activated. That next phase, electrical testing, fluid filling, and calibration, marks a turning point in the assembly process, transitioning the Golf from a mechanical object to a functioning machine. As the Volkswagen Golf continues its progression down the general assembly line, it begins to cross into one of the most critical sections of production: system initialization and functional testing. This stage transforms the vehicle from a silent shell into an electrically alive machine. It is here that the electronic control units, or ECUs, are first brought online. These digital brains govern virtually every function in the vehicle, from fuel injection timing and anti-lock braking response to climate control algorithms and sensor-based driver assistance systems. The Golf contains dozens of these ECUs, each responsible for different subsystems, and all interconnected through a series of high-speed data buses such as CAN, L-Ion, and FlexRay. Before any electrical current is sent through the system, technicians connect the vehicle to a centralized factory diagnostic interface via a port located under the dashboard. The same OBD port later used by service technicians and inspection facilities. Using specialized software, factory workers upload the correct firmware and configuration data into the ECUs. This process is not merely about flashing software. It's about synchronizing every system to the specific build of that vehicle. Variables like engine type, transmission variant, lighting package, regional compliance requirements, and customer-selected options all influence how the ECUs behave. This digital handshake ensures the car will operate correctly and meet both performance and regulatory expectations. Once the ECUs are initialized, the next step is electrical verification. Automated test rigs are used to check that every connection, sensor, and actuator is functioning correctly. These rigs apply voltage and resistance checks through the wiring harness, lighting systems, and control modules. Even minor faults, such as an improperly seated connector or excessive resistance in a wire, are immediately flagged by the system. Any detected issues cause the car to be diverted from the main line to a specialized diagnostic bay where trained technicians perform pinpoint troubleshooting and rework, ensuring that no electrical faults go undetected. Parallel to the electrical system bring-up, the vehicle also receives its initial fill of operational fluids. These include engine oil, coolant, brake fluid, transmission fluid, power steering fluid if hydraulic, and in some cases, refrigerant for the air conditioning system. The filling process is performed by robotic dispensing arms that are pre-programmed to deliver the precise volume and type of fluid required for each model. Flow meters, pressure sensors, and digital records ensure absolute consistency and prevent underfilling or contamination. The fuel tank is also filled with a small amount of test fuel, typically around 5 to 10 liters, sufficient for initial startup, emissions testing, and short-range driving tests later in the process. After fluid filling, one of the most dramatic moments in the assembly process occurs: the engine start. This is not done casually, nor is it done without extensive prior checks. Once all systems are confirmed ready, a technician activates the ignition via the factory diagnostic system or a standard key fob, causing the engine to turn over for the first time. Sensors throughout the vehicle immediately begin transmitting data: engine RPM, oil pressure, coolant temperature, voltage levels, and emission sensor feedback, all of which are monitored live by quality assurance software. If the engine does not start within a certain time window, or if any critical values fall outside the permissible range, the vehicle is automatically flagged for further inspection. Assuming a successful startup, the next phase involves dynamic system checks. These include actuating key mechanical subsystems to ensure proper functionality. The steering is rotated lock to lock to test assist levels and detect any binding. The brakes are pressurized to confirm pedal feel and hydraulic integrity. The transmission is cycled through its gears, with automatic models shifting through each range while stationary, and manual models undergoing clutch engagement tests. Additional functions like power windows, central locking, infotainment screens, headlight alignment, and mirror adjustments are also verified at this stage. All of these checks are conducted on the moving assembly line or at dedicated inspection stations known as end-of-line testers. These stations are equipped with rollers, sensors, cameras, and feedback terminals that allow technicians to observe live data streams. If a vehicle passes all of these checks, it is allowed to proceed to the next major step: wheel mounting and torque application. At this point, the Golf receives its wheels and tires, which have been assembled and balanced in a separate part of the plant. Tire suppliers often work in close partnership with the assembly plant, sometimes even maintaining satellite facilities on site to deliver tires in real time according to the production sequence. The wheels are mounted using robotic arms equipped with torque sensing screwdrivers. These tools are programmed with model-specific torque settings and follow a defined tightening sequence to ensure that every lug nut is fastened uniformly, reducing the risk of vibration or uneven stress on the brake rotors. After wheel installation, the vehicle is lowered off its assembly jigs and finally touches the ground under its own weight. This moment, often called first contact, marks the vehicle's readiness for dynamic testing. It is now fully assembled, fully functional, and ready to move under its own power. But production does not end here. The vehicle is then driven, slowly and under tight controls, to the next area of the plant: the rolling road test bench, also known as the dynamometer station. Here, the car is placed onto a set of rollers that simulate driving conditions while keeping the vehicle stationary. The purpose of this test is to perform a full spectrum functional evaluation under load. The vehicle is accelerated, decelerated, and driven at varying speeds while sensors record engine performance, emissions output, braking effectiveness, and drivetrain behavior. Advanced vision systems check headlight aim and beam shape. Microphones measure cabin noise under acceleration. Even the wiper system is tested using artificial rainfall nozzles while the car is driven at simulated speeds. If any aspect of this test fails to meet Volkswagen's internal benchmarks, the car is again pulled from the line and sent to a rework zone. Here, highly trained specialists diagnose and resolve the issue, whether it be a misaligned sensor, a software glitch, or an out-of-spec component. vehicles cannot proceed to final inspection until they achieve a perfect score on the dynamometer test. Following this dynamic validation, the car enters the final quality inspection area. This zone is brightly lit and staffed with quality control inspectors who perform a visual and tactile examination of every surface, seam, and feature. Paintwork is scrutinized under color-correct lighting to detect any blemishes, orange peel, or dust inclusions. Door gaps and panel alignment are measured with precision gauges. Interior materials are checked for fit, finish, and correct placement. Inspectors open every door, operate every switch, and sit in the car to check for rattles, uneven padding, or installation errors. This is often the first time someone interacts with the Golf as a complete product, and every detail matters. Once the vehicle passes its final inspection, a protective wrap is applied to its most vulnerable surfaces, typically the hood, roof, mirrors, and door edges, to prevent damage during transport. Barcodes and shipping labels are affixed, and the vehicle is driven to the logistics yard, where it joins a massive fleet of completed Golfs waiting for shipment. These yards are organized with incredible precision, with each car's location digitally tracked for efficient loading onto transport trucks or rail cars. While this marks the end of the physical assembly process within the factory walls, the story of each Golf is far from over. It now enters the distribution and logistics phase, a sprawling global network designed to deliver each vehicle to its final destination as quickly and safely as possible. But that segment of the journey involves a separate layer of logistical planning, international coordination, and dealership preparation, all of which merit a detailed explanation of their own. The freshly assembled Volkswagen Golf, now cloaked in its protective transport films and validated through layers of mechanical, electrical, and aesthetic inspections, begins its transition out of the factory environment and into the broader world. This stage, the post-production logistics and distribution process, is a sophisticated dance of real-time tracking, intermodal transportation, and region-specific compliance, all of which are critical to ensuring that each vehicle reaches the correct dealer in the correct configuration and in pristine condition. After final inspection, the Golf is driven from the assembly line to the Vehicle Logistics Center, often located adjacent to the main manufacturing facility. Here, trained drivers guide the vehicles along designated internal roads, maintaining low speeds and following strictly mapped routes to avoid cross-contamination or accidental damage. At the staging yard, vehicles are sorted based on destination markets, production variants, and transport mode. Some will head to domestic dealerships via truck, while others will be loaded onto trains for long-haul land journeys. For global markets, many Golfs are prepared for shipping by sea, making their way to port via specialized car-carrying rail networks. Before any Golf leaves the staging yard, a final scan is performed. Using handheld barcode scanners or RFID readers, workers verify the vehicle's unique VIN, vehicle identification number, against the factory's production records. This cross-referencing ensures that the car has passed all necessary quality gates, has been matched with the correct transportation order, and is headed to the appropriate regional hub. Additionally, certain destination countries require extra compliance steps before a vehicle can legally enter or be registered, such as emissions documentation, safety certification, or region-specific firmware updates to the vehicle's ECUs. These requirements are embedded into the logistics planning software, and vehicles are automatically routed to compliance zones where technicians apply the necessary updates or decals before departure. Once verified and queued, the Golf is prepared for loading onto a transport carrier. For truck transport, specialized vehicle haulers equipped with multi-level ramps are used. These carriers are engineered to accommodate various vehicle sizes while maximizing capacity and maintaining balance for road stability. Loading is conducted with extreme care. Each car is driven up ramps and secured using wheel straps, chocks, or integrated platform locks that prevent movement during transport. Drivers are trained not only in vehicle handling, but also in load balancing, ensuring that the distribution of weight across the trailer complies with legal road limits and mechanical tolerances. For long-distance rail transport, the Golf is moved onto enclosed or open-sided car transport wagons. These wagons can hold up to a dozen vehicles per unit and are designed to withstand the rigors of long-haul journeys across multiple climate zones. Rail is favoured for its cost efficiency and environmental impact, particularly for routes within Europe, where dense rail infrastructure allows cars to be delivered to regional distribution centres with minimal handling. Once the vehicles reach their destination hubs, often located just outside major cities, they are transferred to final mile delivery trucks that ferry them to individual dealerships. When the Golf is destined for international markets outside of Europe, such as North America, Asia, or Australia, it must be transported by sea. This requires loading the vehicles onto large roll-on/roll-off cargo vessels, also known as ro-ro ships. These enormous ships are essentially floating multi-story parking garages, capable of holding thousands of vehicles at once. At the port terminal, cars are driven aboard by logistics personnel who work under tight schedules to fill each ship efficiently. Vehicles are parked according to a precise digital manifest, which maps each car's location by deck, row, and position for accurate unloading at the destination port. Ro-ro shipping requires a high level of environmental control. Vessels are designed to maintain safe humidity levels, minimize exposure to salt air, and prevent the movement of cars in rough seas through a system of tie-down points and loading jacks. Once the vehicle arrives in its destination country, it goes through a process known as port processing. This includes customs clearance, regulatory inspections, and any market-specific modifications. Depending on the country, this might involve the installation of alternative language infotainment software, the addition of local safety equipment like fire extinguishers or first aid kits, or the application of region-specific emblems and badges. Vehicles are once again inspected for transport-related damage, cleaned, and detailed before being sent to the dealership. But while distribution is an essential part of the car's journey, it is merely the final chapter in the broader industrial narrative. To truly understand the full scope of how a Volkswagen Golf comes to be, we must look beyond the visible car to the invisible infrastructure that supports its manufacture, the supplier network, component fabrication, and just-in-time logistics that converge at the assembly plant like veins feeding into a living heart. Every Golf is made up of more than 30,000 individual parts, many of which are produced not by Volkswagen directly, but by a web of Tier 1 and Tier 2 suppliers across the globe. These include suppliers specializing in electronics, seats, glass, tires, injection molded plastics, turbochargers, radiators, axles, and much more. These companies operate under strict quality and timing requirements, often working within a just-in-sequence framework. This means that not only must the parts arrive just in time to avoid stockpiling or shortages, but they must also arrive in the exact order in which they are needed on the line. To enable this, Volkswagen uses a combination of supplier parks, regional distribution centers, and digital planning tools that forecast production demand down to the minute. Many of these suppliers operate satellite facilities on or near the Volkswagen campus itself. These microfactories are tightly integrated into the main production loop. For instance, a seat supplier may receive a digital order moments after a car body is painted and matched to a particular trim level. Within hours, the seat is built, quality checked, and delivered to the assembly line just as the car arrives at the station where it will be installed. The just-in-time system dramatically increases efficiency and reduces warehousing costs, but it also demands precision and resilience. Any disruption in the supply chain, whether due to weather, labor issues, or global events, can ripple across the production schedule. To manage this complexity, Volkswagen employs advanced manufacturing execution systems and enterprise resource planning software that communicate with suppliers, forecast demand, and adjust schedules in real time. Each supplier must adhere to predefined quality protocols, including statistical process control, failure mode analysis, and traceability documentation, which are routinely audited by Volkswagen's internal teams. On the component level, many key parts are manufactured using highly specialized processes before they ever reach the main assembly line. Take, for example, the engine, the mechanical heart of the Golf. Engine blocks begin their life as raw aluminum or cast iron, melted and poured into precision molds using high-pressure casting methods. Once solidified and cooled, the blocks are machined using CNC equipment that drills, hones, and surfaces the bores and mating faces to tolerances often measured in microns. Crankshafts, camshafts, pistons, and cylinder heads undergo similar processes, each passing through multiple heat treatment, grinding, and quality inspection stages before final assembly. The completed engine is then mated with its transmission, tested on a cold bench, a fixture that simulates operation without fuel or combustion, and sent to the main production hall. There, it joins the sequence of drivetrain assemblies that will eventually meet their respective body shells on the marriage line. Similarly, high-tech components like digital dashboards, ADAS sensors, and infotainment head units are built and tested in cleanroom environments to prevent contamination or electrostatic damage. These electronic assemblies are subjected to functional tests, environmental stress simulations, and firmware updates before being sent to the main line. At the plant level, all of these moving parts, mechanical, logistical, and digital, converge into what is often described as a cyber-physical production system. Assembly lines are increasingly governed by AI-enhanced predictive analytics, machine learning algorithms that forecast wear on machinery, and autonomous material handling vehicles that navigate factory floors using LiDAR and GPS. Real-time dashboards allow factory managers to monitor production flow, equipment uptime, part inventories, and worker ergonomics from centralized control centers. Robots, collaborative arms known as cobots, and human workers form a hybrid workforce that constantly adapts to changes in demand, variant complexity, or technological updates. All of this results in a manufacturing ecosystem that is as complex and finely tuned as the vehicles it produces. The Volkswagen Golf, which might appear to the average buyer as a simple compact hatchback, is in reality the output of a global network of suppliers, engineers, robots, and logisticians working in concert with millisecond-level precision. It is a product born of thousands of hands and millions of decisions, every one of them contributing to the moment when the car's engine starts for the first time, the headlights blink to life, and it begins its journey toward the showroom floor. As the story of the Volkswagen Golf continues within the factory walls, we now shift focus to the critical yet often overlooked phase that follows the assembly and functional testing of the physical vehicle. Final calibration, detailed software programming, and human-centered quality control measures that ensure not just mechanical soundness, but also driving experience fidelity, safety compliance, and brand consistency. This stage marks the final opportunity for engineers and technicians to refine the car's personality, the way it feels, sounds, and responds before it ever reaches a dealership. Once the vehicle passes its rolling road test, electrical verification, and cosmetic inspections, it enters what's referred to in modern manufacturing as the calibration and personalization loop. Here, technicians interface with the vehicle's multiple electronic control units, upwards of 50 in many Golf variants, to fine-tune parameters such as steering weight, throttle response, transmission shift points, air conditioning behavior, and even ambient lighting modes. Although these parameters are based on predefined model profiles, small adjustments are often needed to account for tolerances in component performance, environmental conditions, and the specific variant configuration of the vehicle. This process uses a digital toolchain, often referred to as a centralized vehicle configuration system. The technician connects a specialized programming console to the vehicle's onboard diagnostics port. Through this interface, the system retrieves the vehicle's build sheet, a digital summary of every major component, trim level, engine type, and region-specific setting installed during production. Based on this, the technician downloads the relevant firmware packages and configuration profiles from a secure Volkswagen server. These files include calibrations for dynamic systems like ESC, lane keeping assistance, adaptive cruise control, and the steering rack's servo control logic. The software installation itself is performed with high redundancy and validation steps. Each module receives a cryptographic checksum, ensuring the integrity of the code after download. The system then runs a diagnostic sweep, verifying that all ECUs are correctly communicating across the vehicle's CAN and LN bus architecture. Should any module fail to respond or report a checksum mismatch, the vehicle is flagged and removed from the main line for specialized reprogramming in a secure rework area. This level of rigor is necessary, not only to ensure reliability and drivability, but also because these software systems control functions directly linked to passenger safety. Following calibration, the vehicle passes through a sequence of human-led evaluations known internally as sensory audits. In a world increasingly governed by automated inspection and robotic precision, this human touch remains indispensable. Sensory audit teams, often composed of master technicians and experienced inspectors, evaluate things that machines cannot easily quantify. They listen for rattles or unexpected noises while operating various components, apply gentle force to test the feel of buttons and switches, and run their hands along upholstery seams to detect imperfections in fit or material finish. These teams test the firmness of seat padding, assess the resistance in climate control knobs, and verify the damping in the glove box lid's opening motion. This inspection process is not random. Each inspector follows a detailed checklist created for the Golf's specific variant, whether it's a base TSI model or a performance-oriented GTI. Every tactile point of interaction with the driver or passenger is scrutinized. The sound of the door closing, the feedback of the turn signal stalk, the clarity of the infotainment screen. Even the air vents are examined for smooth adjustability and structural integrity. These subtle, almost imperceptible qualities play a vital role in shaping customer perception. They influence whether a driver describes the Golf as solid, refined, or thoughtfully engineered. And Volkswagen knows that these sensory markers directly translate to brand loyalty. Parallel to the sensory audit is a final high-pressure water test. Here, the vehicle is driven into a sealed chamber where it is subjected to a simulated rainstorm, complete with directed nozzles spraying water at high pressure from multiple angles. The goal is to identify leaks around door seals, windshield bonds, taillights, and underbody grommets. As the water jets barrage the vehicle, sensors inside the cabin monitor for moisture ingress, while technicians inspect areas with flashlights and absorbent strips to detect even minute amounts of seepage. Any vehicle that fails this test is returned to a specialized sealing and bonding repair zone where issues are addressed before retesting. Once these final inspections are complete, the vehicle is officially released from production. However, in a modern Volkswagen plant, this release is also the beginning of a data-rich archival process. A complete digital profile of the vehicle, from every torque specification logged during assembly, to the paint batch number, to the firmware version of the braking system, is uploaded to a central database This digital twin acts as a permanent reference for the vehicle throughout its service life. If a recall or service bulletin is ever issued in the future, this record allows Volkswagen to identify not only which vehicles are affected, but precisely what components or subsystems were installed and when. It is also worth noting that many Golf variants are produced with advanced driver assistance systems, which require a final calibration procedure using sophisticated optical targeting tools. This is especially critical for features like lane keeping assistance, traffic sign recognition, autonomous emergency braking, and adaptive cruise control, which rely on a front-facing camera, radar sensors, and sometimes LiDAR. These sensors must be calibrated in relation to the car's central axis, suspension height, and tire circumference. The calibration process is performed in a controlled bay using visual markers, checkerboard targets, and reference panels, positioned at known distances. Specialized software then guides the technician through alignment adjustments and performs a verification routine, simulating input data to test the system's reactions. The factory also considers the growing importance of software updates throughout a vehicle's life cycle. Increasingly, Golf models are being built with over-the-air update capabilities. This means that certain vehicle functions can be improved or corrected remotely without visiting a dealership. To enable this, each vehicle must be registered with Volkswagen's secure update server and fitted with a telematics control unit capable of handling encrypted data downloads. Before leaving the plant, the vehicle undergoes a brief connectivity test using a private cellular or Wi-Fi network. This ensures that the vehicle can receive updates in the field and that the security keys assigned during factory programming are valid and authenticated. Another major focus of final stage production, particularly in recent years, is environmental sustainability. Volkswagen has implemented comprehensive measures to reduce the ecological footprint of Golf manufacturing. For example, paint shops, traditionally among the most energy-intensive and pollutant-heavy parts of vehicle production, now use water-based paints and advanced overspray capture systems to reduce volatile organic compound emissions. Waste heat from ovens and drying tunnels is recovered and recycled into the factory's climate system. Water used in the electrocoating and wash booths is treated on-site and reused in a closed-loop system. Powering the factory itself is a growing area of environmental emphasis. Many of the plants where the Golf is manufactured have transitioned to renewable energy sources, such as wind or hydroelectric power. In Wolfsburg, for instance, Volkswagen has partnered with regional utilities to supply the production lines with green electricity. Additionally, automated lighting, motion sensors, and energy-efficient drive systems on robots and conveyors contribute to reduced overall consumption. These investments not only lower the per-vehicle carbon output, but also align with Volkswagen Group's broader Way to Zero strategy, a commitment to climate-neutral mobility and carbon-neutral production by 2050. Within the plant, materials management is handled with sustainability in mind as well. Steel and aluminum scrap generated during stamping operations are carefully sorted, compressed, and sent to recycling centers, some of which are reintegrated back into the supply chain. Plastics from production offcuts or rejected trim parts are ground down and reused in non-visible components. Even packaging materials used to deliver parts, such as crates, dividers, and protective films, are tracked and returned to suppliers in a closed-loop logistics model. What makes the Volkswagen Golf's production so remarkable is not just the car itself, but the systems, philosophies, and technological ecosystems that produce it. Each vehicle embodies the cumulative effort of thousands of hours of engineering, years of supplier relationships, terabytes of design simulations, and millions of precisely orchestrated manufacturing movements. What rolls off the line is not a standalone product. but the physical representation of a global, highly optimized industrial organism. One designed to balance quality, efficiency, innovation, and sustainability in every nut, panel, circuit, and drop of fuel or electricity it consumes. As we move deeper into the Volkswagen Golf's manufacturing story, we begin to explore the systems behind the systems, the cutting-edge technologies and organizational strategies that elevate Golf production beyond traditional automotive assembly. Much of this innovation centers around Volkswagen's use of modular platforms, intelligent factory automation, and advanced data analytics, all of which have transformed not just how a Golf is made, but how efficiently, flexibly, and sustainably it can be produced, alongside a range of other vehicle models. At the core of this evolution is Volkswagen's MQB platform, short for Modulare Kurbaukasten, which translates to Modular Transverse Matrix. Introduced in the early 2010s, this platform underpins not only the Golf, but also a wide range of vehicles across Volkswagen Group's brands, including the Audi A3, Seat Leon, and Skoda Octavia. The brilliance of the MQB platform lies in its standardized architecture. Critical hard points, such as the position of the engine, the distance between pedals and front axle, and mounting locations for crash structures, are fixed across models, while allowing flexible variation in wheelbase, track width, and body style. This enables massive economies of scale and allows the Wolfsburg plant, among others, to produce multiple models on a single line with minimal retooling. In practice, this means that a Golf might be built on the same line as a Tiguan or a Touran, using many of the same robotic stations, fastening tools, and software configurations. Tooling carts, parts bins, and robotic arms are designed with adaptability in mind. Instead of having separate jigs for each model, multifunctional fixtures and programmable robots detect the incoming body type via RFID tags or QR codes and adjust themselves in real time. A welding robot, for example, might apply different sequences or torque levels, depending on whether it is working on a Golf hatchback or a longer wheelbase estate model, all without human intervention. This production flexibility is supported by a sophisticated manufacturing execution system, a digital nervous system that tracks every car's status as it moves through the factory. Each vehicle is assigned a digital build order, stored in a centralized database and updated in real time. This build order contains detailed instructions for every station: which components to install, what software to flash, how to calibrate sensors, and which quality checks to perform. At each workstation, screens display the relevant data for the technician or robot, and barcode or RFID scanners confirm that the correct parts are being used before the system allows the job to proceed. The use of artificial intelligence and machine learning is increasingly embedded into this ecosystem. For instance, predictive maintenance systems monitor vibration, temperature, and performance data from thousands of robots, conveyors, and tools in real time. If a welding robot's arm begins to show early signs of wear, even imperceptible to human operators, the AI flags the issue and schedules preventative maintenance before failure can occur. This predictive approach significantly reduces downtime and helps maintain the tight production cadence that modern car manufacturing demands. Another area where AI plays a pivotal role is in vision systems and quality control. High-resolution cameras paired with deep learning algorithms are used throughout the assembly and inspection processes. These systems are trained on thousands of images to identify correct panel alignment, paint consistency, weld seam quality, and even minute cosmetic defects. In the paint shop, for example, the system can detect a single dust particle trapped in a clear coat, then alert technicians to isolate the cause, whether it's an air filtration issue, static charge on the body panel, or improper cleaning upstream. These insights are logged and used to refine both the hardware and the process over time, feeding back into a continuous improvement loop. But AI is not just about machines replacing human oversight, it's about augmenting human decision-making. In interior assembly, where more variation exists due to trim-level complexity, workers are assisted by augmented reality headsets that project assembly instructions directly into their field of view. These AR systems highlight where each clip, fastener, or electrical connector should go and can overlay 3D models of correct placements onto the physical work area. If the system detects a potential mismatch, such as a left-hand drive HVAC control unit being installed in a right-hand drive model, it alerts the worker before the part is fully installed. This not only reduces errors, but empowers technicians to handle more complex tasks without relying solely on memory or printed documentation. All of these advancements contribute to a concept Volkswagen refers to as smart production, an overarching philosophy that treats the factory not as a static facility, but as a living, evolving system. This philosophy is particularly evident in how Volkswagen manages its energy consumption, materials flow, and human ergonomics. For example, autonomous guided vehicles have largely replaced traditional forklifts and trolleys in many areas of the Golf's production. These AGVs navigate using a combination of magnetic strips, LiDAR, and real-time mapping, delivering parts from storage zones to the assembly line on demand. This reduces congestion, minimizes human error in part selection, and allows the line to adapt more fluidly to shifting production priorities. From an energy standpoint, smart production integrates intelligent building management systems that adjust heating, cooling, and lighting based on real-time occupancy and environmental data. Robots enter standby mode when idle for more than a few seconds. Compressed air systems, traditionally one of the most energy-intensive parts of any industrial plant, are monitored by AI that optimizes pressure delivery to exactly what is needed, exactly where it is needed, with zero excess. These micro-optimizations, when multiplied across thousands of systems and millions of cycles per year, contribute to measurable gains in sustainability. Ergonomics and human factors are also key to this philosophy. Every workstation on the Golf assembly line is designed to reduce strain, fatigue, and injury. Adjustable platforms allow workers to bring the vehicle to an optimal height depending on the task. Overhead, assist arms support the weight of heavy tools, reducing the need for muscle force. Color-coded part trays, automatic torque wrenches, and real-time feedback screens help workers maintain quality while minimizing the mental load of memorizing dozens of process steps. Additionally, Volkswagen invests heavily in worker training, offering digital simulators, VR-based assembly previews, and rotating task assignments to improve skill versatility and maintain high morale. This combination of human-centered design and intelligent automation also allows the Golf production line to be highly responsive to changing market demands. If a sudden spike in orders for a particular trim level occurs, say the Golf GTI with a sunroof and adaptive suspension, the MES system can reprioritize the build queue, notify suppliers of increased part demand, and adjust the workstations along the line in real time. Robots recalibrate their movement patterns, AGVs update their delivery routes, and workers are presented with new instructions through their digital displays. What once would have required days or weeks of retooling now happens in hours, or in some cases, minutes. One of the most compelling outcomes of these systems is Volkswagen's ability to maintain quality parity across global production sites. Thanks to centralized data systems, a Golf built in Wolfsburg can be virtually identical in build quality and performance to one assembled in Puebla, Mexico, or Changchun, China. Volkswagen uses digital twins of its production equipment, virtual replicas that simulate and mirror real-world machines, to replicate best practices across all facilities. If a process optimization is discovered in one plant, such as a more efficient adhesive application method or a faster sensor calibration routine, that improvement can be tested digitally, validated, and then rolled out to other sites via secure updates to their MES software. All of these advancements are not just about building a better car. They're about building a better manufacturing system, one that is scalable, adaptable, and forward-compatible. This is especially important as the automotive industry transitions to electrification. The Golf, as of the latest generation, shares many of its production processes with Volkswagen's ID family of electric vehicles, while the ID.3 and ID.4 are built on a separate platform, MEB. The lessons learned from MQB production, including robot versatility, flexible logistics, and digital calibration, are directly transferable. In fact, many stations within the same factory can now switch between building a combustion engine Golf and an electric vehicle, with only minor tooling changes and software adjustments. Volkswagen's approach to production is ultimately one of modular intelligence, a blend of standardized hardware, reconfigurable software, and scalable systems that can evolve with the demands of new technologies, consumer preferences, and global regulatory changes. And in this sense, every Golf rolling off the line is not just a vehicle. It's a node in a vast, intelligent, and continually learning machine. The story begins not on the road, but on the factory floor, though in truth, the first chapter is even earlier than that. Before a single part enters the factory gates, long before assembly lines begin their rhythmic dance, engineers and designers at Harley-Davidson's Product Development Center in Wisconsin have already been at work for years. Each new model starts as a digital blueprint, forged by design software and creative minds. Here, the shape of the tank, the rake of the forks, the lean angle, the exhaust note, and even the ergonomic geometry of the handlebars are carefully modeled and simulated. Engineers use computer-aided design and finite element analysis to simulate stress, fatigue, and aerodynamics, ensuring that the final product won't just look good, it will perform flawlessly under a wide range of real-world conditions. Once the final design has passed simulation, stress testing, and review, it's time to move into pre-production and sourcing. Harley-Davidson relies on a complex global supply chain to feed its production facilities with raw materials and pre-machined components. High-grade steel, cast aluminum, rubber compounds, wiring harnesses, and precision fasteners are sourced from vetted suppliers. But Harley doesn't simply receive and use these materials without scrutiny. Every incoming shipment undergoes rigorous inspection through quality control departments. Metallurgical testing ensures that the steel meets tensile and corrosion resistance requirements. Aluminum castings are X-rayed for internal voids or inclusions. Fasteners are torque tested and rubber components are aged artificially to assess long-term resilience. Only after passing these controls are the components allowed to enter inventory for production use. With materials in place and quality assured, the next phase begins at the Harley-Davidson Powertrain Operations Plant, located in Menominee Falls, Wisconsin. This facility is where the heart of every Harley, the engine, is born. The engine build process begins with crankcase machining. A raw aluminum casting arrives at a CNC machining center, where robotic arms load and secure the case onto multi-axis spindles. Coolant sprays hiss and mist into the air as the machine carves bearing journals, oil galleries, and bolt passages with surgical precision. Each crankcase half is machined to tolerances within a few microns, then measured using coordinate measuring machines to ensure dimensional perfection. Next comes the assembly of the rotating assembly. The crankshaft is balanced dynamically on a computerized balance machine. Each counterweight is drilled or weighted until the crankshaft spins within an exact imbalance threshold, reducing engine vibration. Connecting rods forged from high tensile steel, are then matched in weight and attached to the crank using precision ground bearings. This subassembly is then mated to the camshaft and timing components, either a push rod setup for traditional big twins or a more modern overhead cam design depending on the engine family. Cylinder barrels, typically cast from aluminum and lined with Nicosil or iron sleeves, are bored and honed using high-speed diamond tooling. Pistons are inserted using pneumatic jigs that ensure proper ring alignment and skirt lubrication. Once the top end is mated to the lower end, the valve train is installed. This includes lifters, push rods or cam followers, rocker arms, and valve springs, all carefully pre-lubricated with assembly grease. Each engine is built by a small team of trained technicians who work in dedicated cells rather than traditional assembly lines. This modular production system allows for greater accountability and ensures that each technician develops specialized expertise. Before moving on, every assembled engine undergoes a series of tests. A cold test involves spinning the engine using an electric motor, allowing technicians to measure oil pressure, compression, and resistance without firing it. Once it passes this stage, the engine is placed in a test cell and run live, briefly but rigorously. Sensors measure exhaust composition, vibration signatures, and thermal stability. Only after passing this battery of diagnostics does the engine earn a serialized identification plate, etched with its unique build number. That number will follow the engine through the rest of the factory and ultimately out into the world. With the engine complete, we move next to the vehicle assembly plant in York, Pennsylvania. This is where the soul of Harley-Davidson, the engine, is married to its physical frame. But before that union can happen, the frame itself must be constructed. Unlike many motorcycle manufacturers that weld frames overseas, Harley still fabricates and welds its steel frames domestically. Long steel tubing is precision cut using automated lasers, which not only slice the material, but also etch alignment marks and create bracket slots. These tubes are then positioned into robotic welding fixtures that use vision-guided arms to lay down consistent welds along every joint. This automated welding ensures uniform strength and aesthetic consistency, even in hidden seams. After welding, the frames undergo a multi-stage cleaning and coating process. First comes degreasing and alkaline washing to remove oil and metal particles. Then the frames are dipped into a phosphate bath to improve paint adhesion. Finally, they are moved through an electrocoating line where the entire frame is submerged in a bath of electrically charged paint particles. This process, known as e-coating, ensures that even interior surfaces of the frame are protected from corrosion. The coated frame is then baked in a curing oven where the finish hardens into a tough, chip-resistant shell. As the baked frames cool, they are conveyed to the beginning of the assembly line, where initial sub-assemblies are installed. This includes mounting engine brackets, isolator bushings, and drivetrain mounts. Then, using a hydraulic hoist, the freshly built engine is carefully lowered into the cradle of the frame. Specialized jigs hold everything in alignment while technicians bolt the power plant into place. This is a pivotal moment in the production process. The raw components now begin to take on the form of a living machine, but we're only scratching the surface. Over the next few thousand words, we'll dive into the complex sub-assemblies that follow: suspension setup, wiring harness routing, fuel system integration, exhaust plumbing, wheel mounting, brake system pressurization, instrument calibration, and the all-important rolling road tests. Each of these steps is performed with precision, using a combination of human skill and cutting-edge automation. The deeper we go, the more you'll see that behind every Harley-Davidson motorcycle is an orchestra of craftsmanship, robotics, material science, and tradition, working together to create a machine that is both muscle and mythology. With the engine now seated into its steel cradle, the motorcycle's skeleton begins to take on structure and intent. But a machine is more than metal. It needs electricity to live, to breathe, to communicate with its rider and its environment. At this stage of production, the electrical harnesses are carefully routed through the frame. These harnesses serve as the central nervous system of the motorcycle, carrying signals and power to every key component: the ignition system, lighting, control modules, sensors, and display interfaces. Each wiring harness is pre-manufactured in a separate sub-assembly area. Workers use modular jigs to route and tape bundles of copper wires, each precisely color-coded and crimped with terminals at connection points. The harnesses are labeled with laser-etched heat-shrink tubing for traceability. Before installation, every harness undergoes a continuity test. Hundreds of pins and connectors are checked electronically to confirm that signals will flow without interruption or short circuit. Then installers begin the delicate task of threading these harnesses through the narrow channels and cavities of the motorcycle's frame. The process is far from random. Technicians follow model-specific routing paths that are standardized for each bike family. Certain wires are routed through rubber grommets to prevent chafing. Others are wrapped in heat-resistant sheathing near engine components. All connectors must be aligned and torqued to factory specifications to ensure long-term durability. It's a job that requires dexterity, patience, and precision. A misrouted wire could mean a malfunction in the ignition, or worse, a failure in lighting or braking systems under load. With the electrical backbone installed, it's time to mount the control modules. These include the Engine Control Unit, or ECU, which manages fuel injection, ignition timing, and emissions controls. Harley-Davidson ECUs are pre-programmed with model-specific maps and self-diagnostic logic. The ECU is mounted within a sealed compartment, often underneath the seat or side covers, protected from vibration and water ingress. Other modules, such as the body control module and ABS controller, are also installed at this stage. Now comes one of the most physically intensive phases of the assembly process: suspension and wheel integration. The front forks, typically telescopic in design and filled with oil-damped cartridges, arrive from a dedicated supplier or are assembled in-house. These fork assemblies are mated to the steering head using tapered roller bearings and a triple tree clamp. Technicians use a digital torque wrench to secure the steering stem nut, ensuring precise rotational resistance without impeding handlebar movement. Once the front end is secured, the rear swing arm is mounted. This component, usually made of forged aluminum or steel tubing, is responsible for holding the rear axle and suspension linkage. Pivot points are greased and sealed with polymer bushings or needle bearings. Twin or monoshock absorbers are then mounted, depending on the model. Modern Harley-Davidson suspension systems are often preload adjustable, allowing riders to fine-tune comfort based on load and terrain. Wheels are next, and these are not just functional, they are also aesthetic centerpieces. Each wheel begins life as a forged or cast aluminum blank, CNC machined to tight tolerances, and then powder-coated or chrome-plated for a long-lasting finish. The tires are mounted and balanced in a separate cell using automated tire changes and dynamic balancing machines. Wheel assemblies are then brought to the main line on just-in-time carts, tagged and matched by VIN to ensure compatibility. Installation of the wheels requires precise alignment. The front axle is slid through the fork sliders and torqued with spacers that position the wheel perfectly between the brake calipers. The rear wheel installation is more complex as it involves the final drive system. Depending on the model, this could be a belt drive or chain drive. Most Harley-Davidson cruisers use a carbon-reinforced final drive belt, which is quieter and lower maintenance than a traditional chain. The drive belt is looped over a rear pulley mounted to the wheel hub and then connected to the front pulley attached to the transmission output shaft. Proper tensioning of the belt is critical. Technicians use a belt deflection gauge to measure vertical play and ensure that alignment marks on the swing arm are symmetrical. A misaligned belt could cause vibration, premature wear, or even catastrophic failure at high speeds. At this point, the motorcycle is capable of supporting its own weight and can roll under its own momentum, but it still lacks the ability to stop. The braking system is the next critical component to be installed. Harley-Davidson motorcycles typically use hydraulic disc brakes, with calipers provided by trusted OEM partners such as Brembo. Rotors are bolted onto wheel hubs using high-torque fasteners and thread locker to prevent loosening under thermal cycling. The calipers are mounted on fixed or floating brackets, and the hydraulic lines are routed from the hand and foot controls to the master cylinders. Stainless steel braided brake lines are common on high-end models, offering better heat resistance and reduced expansion under pressure. Each brake line fitting is tightened and checked for leak resistance using vacuum testers. Once assembled, the entire brake system is filled with DOT-approved fluid and bled using automated vacuum bleeders. These machines draw fluid from the reservoir and force it through the entire system, removing air bubbles and ensuring consistent lever feel. Braking force is tested on a rolling dyno, where the motorcycle is accelerated and decelerated repeatedly to simulate real-world stopping forces. Now, we move on to fuel system installation. The fuel tank is often one of the last major structural components to be installed because of its size and central placement. Each tank is stamped from sheet metal using hydraulic presses, then welded and pressure tested in a sub-assembly area before being painted and finished. The tank includes mounts for the fuel pump, fuel level sensor, and filler cap. The fuel pump is a critical component, capable of maintaining consistent pressure to feed the injectors even at high throttle openings. Technicians install the tank using rubber isolation mounts to minimize vibration transfer to the rider. The fuel lines, typically made of multi-layered plastic with quick disconnect fittings, are routed and locked into place. At the same time, the intake manifold and throttle body are installed. On modern fuel-injected Harleys, the throttle-by-wire system replaces mechanical cables, sending rider input as digital signals to the ECU. The exhaust system is now ready to be fitted. Composed of multiple segments including headers, catalytic converters, mufflers, and sometimes heat shields, the exhaust system is both a functional and stylistic element. Headers are aligned with the exhaust ports on the engine and bolted using copper gaskets and torque-sensitive fasteners. The entire assembly must be leak-free to ensure proper scavenging and emissions compliance. Many exhaust sections are clamped rather than welded, allowing for slight thermal expansion and easier serviceability. Every muffler is sound tested in a pre-install inspection cell. This ensures that it meets both aesthetic tonal requirements, the signature Harley rumble, and legal decibel limits. Engineers spend countless hours designing baffling systems that produce that deep, throaty growl without exceeding emissions and noise regulations in different markets. At this stage, the motorcycle is structurally complete. It has a mounted engine, operational suspension, braking capability, an installed drivetrain, and a connected electrical system. But before it's ready to run, a suite of onboard diagnostics and calibrations must be performed. Using a factory service terminal, technicians connect directly to the ECU to upload the final firmware package. This includes the ignition map, rev limiters, idle calibration, and any region-specific emission profiles. Each system, ABS, traction control, cruise control, ride-by-wire throttle, is calibrated and tested using diagnostic software. Parameters are recorded and logged against the motorcycle's VIN. Finally, before any cosmetic trim or finishing components are added, the motorcycle is taken to the test station for its first moment of life, an initial ignition and run test. On the test platform, the motorcycle is clamped into a stationary cradle, where it can be run through all gears under simulated load. The technician starts the engine and lets it warm up, listening for unusual noises, rattles, or misfires. Exhaust gases are analysed for emissions compliance. Gear shifts are tested through clutch and throttle input. This is where all the invisible systems, ECU logic, fueling maps, sensor data, prove their reliability. The engine has roared to life. The electrical systems are live, the brakes bled and tested, the suspension calibrated, and the wheels balanced. But standing at this stage on the assembly line, the motorcycle still lacks its visual identity. The silhouette is skeletal, lacking the flowing fenders, detailed trim, headlight nacelle, and signature tank emblem that turn a machine into a Harley-Davidson. It's here that we begin one of the most visually transformative phases of the process: the installation of bodywork and cosmetic components. Before any part is mounted, each painted piece must pass through Harley-Davidson's state-of-the-art finishing facility. The company takes immense pride in its paintwork, arguably among the best in the industry, and every tank, fender, and panel is treated as a work of industrial art. The process starts with raw metal surfaces that have been e-coated earlier to resist corrosion. These parts are cleaned again in a dust-free environment, then electrostatically coated with a primer layer that serves as the base for adhesion and color consistency. Each part then moves into one of several high-tech paint booths where robotic arms spray base coat, mid-coat, and clear coat in precise succession. Color is applied in thin, overlapping passes to avoid sagging or orange peel. Some special edition models or custom schemes may receive hand-laid pinstriping or airbrushed accents by trained artists. Once painted, parts are cured in a multi-zone baking tunnel where temperatures are tightly controlled to ensure gloss retention and film hardness. After curing, every surface is polished by hand with rotary buffers to bring out maximum depth and brilliance. The painted fuel tank, perhaps the most visually iconic part of any Harley, is the first to be installed. Technicians lift the tank using padded jigs to avoid blemishing the finish. Before mounting, they inspect the tank's underside for any imperfections or debris. Then the tank is carefully lowered onto its rubber isolation bushings, aligned with locator pins, and bolted to the frame. The fuel line is reattached, and the fuel pump connector is locked in place. Special attention is paid to clearance around wiring harnesses, vent lines, and control cables. Next, the front and rear fenders are installed. These parts do more than just protect against road spray. They shape the entire look and character of the bike. A chopped fender might suggest a lean, aggressive stance. A full-skirted fender evokes heritage and luxury. Each fender is mounted using stainless steel fasteners and lock washers, torqued to precise specs to avoid cracking the painted surface. Rubber washers are sometimes used between the mount and the frame to dampen vibration and preserve paint integrity. Once the major body panels are in place, attention turns to the lighting system. The headlamp assembly is a critical component, not only for function, but also for styling. On many models, especially touring and cruiser variants, the headlight is enclosed in a nacelle, a chrome or blacked out housing that integrates seamlessly into the front forks and handlebars. The headlamp itself may use halogen, LED, or even adaptive lighting systems that shift beam patterns based on lean angle and speed. Installation begins by mounting the nacelle brackets and then inserting the headlamp housing. Electrical connectors are fitted with dielectric grease to resist corrosion and ensure continuity. The lamp is aligned using built-in adjusters to meet DOT or ECE aiming specifications. Technicians use a laser-based aiming tool to confirm the beam falls within acceptable tolerances for height and direction. Signal lights and running lights are installed next, often integrated into the front forks or handlebar controls. Moving to the rear, the taillight and turn signal assemblies are mounted onto the fender struts or saddlebags, depending on the model. These lighting units are pre-wired and sealed at the sub-assembly stage. Like the front, each connection is tested for voltage and function. The brake light is tested under real pedal pressure to confirm actuation at the proper threshold, and flash rates for turn signals are measured against onboard BCM calibration settings. The license plate bracket is installed last among the lighting and rear accessories. Often integrated with its own light source, this part must be carefully positioned to comply with legal visibility angles and avoid interference with saddlebags or rear suspension travel. At this point, the motorcycle is nearly complete, but no Harley-Davidson would be roadworthy or rideable without its seat. The seat is more than a cushion, it's a functional interface between rider and machine. Seat pans are molded from high-impact polymers or lightweight steel and covered in marine-grade vinyl or leather. High-end models may include gel inserts or memory foam layers for long-distance comfort. Each seat is designed with specific ergonomics, reach zones, and hip contouring based on anthropometric data collected over decades of rider feedback. The seat is installed by engaging a rear-mounted tab and securing the front portion with a key lock or bolt system, depending on the bike. Technicians check for fitment, ensuring no gaps exist between the tank and the leading edge of the seat. Passenger seats or pillions are installed similarly and checked for symmetry. After the seat is in place, final trim pieces are added. These include side covers, battery box panels, derby covers, chain guards, and in some cases, cosmetic engine covers. These parts are usually injection molded ABS or aluminum and are secured using hidden fasteners or quick release systems. Each piece is both decorative and functional, often doubling as protection for wiring or key service access points. Now the motorcycle moves into a critical transition phase, initial cosmetic inspection. In this quality checkpoint, a team of inspectors armed with LED lighting hoods and magnifiers examine every inch of the bike for visual defects. They look for paint imperfections like fisheyes, orange peel, or dust nibs. They check alignment of body panels, gaps between tank and seat, symmetry of handlebar controls, and cleanliness of chrome surfaces. Finger smudges, mist adhesives, or uneven decals are all flagged and corrected on the spot. A unique feature of Harley-Davidson's production process is that each motorcycle's fit and finish is reviewed against its specific build sheet. Because the company offers a high level of customization, from handlebars to wheels to finished kits, each bike may vary slightly. This makes standardization of cosmetic inspection more complex and more important. Once the motorcycle passes the cosmetic audit, it enters what is known as final torque verification. This step is about precision assurance. Technicians, guided by model-specific torque charts, use digitally calibrated wrenches to retorque all critical fasteners, axle nuts, triple clamp bolts, handlebar risers, engine mounts, and foot control brackets. Each torque reading is recorded electronically and tied to the motorcycle's VIN, creating a digital record of mechanical compliance. In parallel, a second technician performs functional testing. They verify the responsiveness of hand controls, including throttle-by-wire actuation, clutch lever pressure, and brake lever feel. Switchgear functions, kill switch, starter button, turn signal toggles, horn, are tested systematically. The instrument cluster is checked for backlight consistency, diagnostic warning lights, and correct display of odometer and gear indicator. Mirrors are mounted and adjusted. Windshields, if included, are secured with vibration damping grommets. Accessory mounting points are confirmed against the bike's configuration. Some bikes may leave the factory pre-wired for accessories like heated grips or auxiliary lighting. The motorcycle is gleaming beneath factory lights, its body panels polished, its engine warmed and calibrated, and its components torqued to spec. But no Harley-Davidson ever leaves the production line without first proving itself on the dyno, the rolling road test. This is the moment where the factory simulates the real world, where the motorcycle earns its first taste of motion under its own power. It's not just a test, It's a rite of passage. Each assembled motorcycle is wheeled to a secure dyno bay within the plant. These test cells are acoustically isolated and engineered for safety, with heavy-duty ventilation systems to manage heat and exhaust. The dyno setup consists of large, motor-driven rollers embedded in the floor. The front wheel is secured in a clamp, and the rear wheel rests on the rollers. Technicians strap the motorcycle down using tension-rated webbing at the front forks and frame rails. Sensors are clipped to the wheels and frame to measure rotational speed, torque output, vibration, and response under load. Before ignition, technicians input the VIN into the dyno computer system, which loads a specific test profile for that bike's model and configuration. Different models undergo different tests. A Sportster with a short-stroke engine is evaluated for fast throttle response, while a touring bike with a Milwaukee 8 V-twin might be tested more rigorously for heat soak and long-duration performance. With the sequence loaded, the ignition is switched on and the engine is fired up. The sound that erupts is unmistakable, deep, pulsing, and resonant. The dyno technician engages first gear and the test sequence begins. The rollers accelerate and the engine climbs through its rev range under calculated resistance. The test mimics stop-and-go city traffic, highway cruising, sudden acceleration, and even simulated hill climbs. All the while, the motorcycle's computer is collecting data: throttle position, air-fuel ratio, ignition timing, and cylinder head temperatures. The technician monitors these parameters in real time on a multi-screen interface. Any deviations from expected behavior, misfires, flat spots in the power curve, hesitation, or excess vibration trigger alerts. In most cases, the test runs smoothly. But if something feels off, even slightly, the technician has the authority to pull the bike from the line and route it to a diagnostic cell for in-depth analysis. Harley-Davidson's policy is strict. No motorcycle proceeds to final packaging until it passes dyno testing without compromise. Following the rolling road test, the bike is shut down and allowed to cool. While that happens, technicians begin the emissions calibration process, which is especially important for export models. Global regulations vary significantly, and Harley-Davidson must comply with emission standards in dozens of countries, from the United States to the European Union to Japan and beyond. To perform emissions calibration, a special sniffer probe is inserted into the exhaust pipe, and the engine is run again under controlled conditions. The system measures hydrocarbons, nitrogen oxides, carbon monoxide, and carbon dioxide in real time. The ECU may receive slight software tweaks during this phase to bring emission levels within regulation while maintaining performance and sound quality. This is a delicate balance. Excessive leaning of the air-fuel mixture to reduce emissions can cause engine hesitation or overheating. Harley's engineers walk this tightrope using dynamic adjustment algorithms built into the ECU software. Next, the motorcycle is routed to the fluid check and top-off station. While many fluids have already been added earlier in the process, brake fluid during system bleed, engine oil during assembly, this station ensures that levels are perfect and that all fluids are clean and uncontaminated. A technician first checks the engine oil using a digital dipstick tool that provides an instant readout. If the oil is slightly low due to fluid settling after dyno testing, it's topped off using metered dispensers connected to an overhead supply system. Transmission fluid or primary drive oil is checked next, depending on the model. For belt-driven cruisers with a separate primary case, the fluid level is measured via inspection ports and sight glasses. The technician uses a clean syringe-style pump to adjust fluid levels within a narrow tolerance window. Overfilling could cause clutch drag. Underfilling could cause overheating and premature wear. Coolant is verified on models equipped with liquid cooling, especially some Sportster and Pan America variants. A pressure cap tester is used to ensure the system is sealed and the radiator or reservoir is topped off with pre-mixed coolant. Finally, the fuel system is partially filled with a low volatility test fuel, just enough for startup, emissions verification, and loading onto transport. Full tank fills are typically left to the dealership or end user for safety during shipment. Now that the fluids are confirmed, the motorcycle is cleaned one final time before final inspection. Any fingerprints, grease, or protective film residue is removed using lint-free cloths and pH-balanced cleaning sprays. A UV inspection light is used to reveal invisible residues or micro scratches in paint and chrome. The wheels are polished, the seat is checked for alignment, and all visible fasteners are rechecked for torque markings, small painted indicators that verify the fastener has been torqued and inspected. The motorcycle then moves into the final inspection bay. Here, a multi-person team performs a top-to-bottom audit of the entire machine. This is the most stringent quality gate in the factory. Every subsystem is reviewed again: lighting, horn, indicators, brake light response, throttle return speed, instrument cluster readout, gear engagement, and idle quality. Inspectors use checklists and standardized procedures to verify that no steps were missed and that the bike meets all internal specifications. Any item that fails to meet expectations results in an immediate halt, with the bike redirected to a quality hold station for correction. Once the motorcycle passes this audit, a final approval tag is attached to the handlebars, listing the names or ID codes of every technician who touched the machine at each station. This chain of accountability is central to Harley-Davidson's quality culture. Technicians take personal pride in the bikes they help build, and this tracking system reinforces ownership over the work. The bike is now ready for shipment, but not before one last process: protective crating. While Harley-Davidson motorcycles are built to endure weather, vibration, and abuse, the company goes to great lengths to ensure that the bikes arrive at dealers in showroom condition. To prepare for crating, a protective film is applied to key surfaces: chrome exhaust pipes, painted fenders, instrument clusters, and fuel tanks. Mirrors are folded or removed. Some handlebars are partially loosened and pivoted inward to reduce overall crate dimensions, especially for international shipments. The motorcycle is then rolled onto a custom steel skid base with welded brackets designed to match the specific model's dimensions. The wheels are locked into place using chocks, and frame anchors are strapped down to prevent movement in any direction. Once secured, a custom-formed steel or composite crate frame is attached around the bike, and a reinforced cardboard or plywood exterior is fixed over the top. Inside the crate, an envelope is attached containing the owner's manual, final inspection certificate, key fob, and any model-specific documentation. Every crate receives a barcode label and RFID tag, which allows it to be tracked in real time through the company's global distribution network. At this stage, the bike is no longer part of the factory inventory. It is now part of a logistical journey that will take it from the manufacturing floor to showrooms, dealers, and eventually riders around the world. Forklifts then load the crated motorcycles onto waiting trailers or shipping containers, depending on their destination. For domestic distribution, the motorcycles are often sent by truck to regional depots and Harley-Davidson dealerships. For international markets, crates are consolidated at export hubs and loaded onto cargo ships or air freight, complete with customs declarations and compliance documentation for the target country. Even after it leaves the factory, Harley-Davidson tracks each motorcycle's journey using its internal logistics system. Dealers receive updates as their allocated bikes leave the plant, arrive at distribution centers, and are scheduled for final delivery. And when the crate is finally opened at the dealership, it marks the last step in a vast and intricate process, a culmination of human hands, robotic precision, global logistics, and over a century of motorcycling heritage. As the crate leaves the Harley-Davidson manufacturing facility, it begins a transition from production unit to consumer product. Whether it's heading to a dealership in Milwaukee, a showroom in Madrid, or a custom shop in Tokyo, the motorcycle enters a highly coordinated logistical network. From this point forward, every minute of the journey is tracked to ensure timing, condition, and destination accuracy. Domestically, crated motorcycles are typically transported by dedicated flatbed trucks or enclosed trailers, operated by Harley-Davidson's contracted carriers. These trucks are climate-controlled and fitted with air ride suspension systems to minimize road vibration and mechanical stress. Crates are arranged in tight configurations, often stacked with reinforced supports to prevent shifting. Each truck is GPS monitored, and arrival schedules are transmitted digitally to regional distribution centers and dealers. For international shipments, the process involves more complex routing. Crated motorcycles are consolidated at export hubs, large warehousing facilities near major ports or airports. Here, the crates are inspected once more for exterior damage, weighed, and manifested according to international customs regulations. Each crate is affixed with documents detailing the vehicle's country of origin, engine displacement, emission certification, and compliance marks such as the CE stamp for European markets. Most international Harley-Davidson motorcycles travel by container ship, secured inside 20 or 40-foot containers along with other motorcycles bound for the same region. Inside the container, crates are anchored to steel D-rings welded into the container floor. Temperature and humidity monitors are often placed inside these containers, especially for long-haul routes that may experience tropical heat, sea moisture, or frigid northern climates. These environmental monitors allow Harley's logistics team to track conditions in transit and identify risks to finish or components. In some urgent cases, such as limited edition releases, VIP orders, or international press events, bikes are air freighted. In this case, the crated motorcycles are loaded into ULDs and flown as cargo aboard commercial or chartered airliners. Upon landing, customs agents review the documentation, and the crates are transferred to local distribution arms that handle last-mile delivery to dealers. Regardless of how it travels, the moment the crate arrives at a Harley-Davidson dealership, the responsibility shifts to the dealership's service and setup teams. Receiving a new Harley is no casual affair. Each crate represents a valuable, serialized product tied to specific order configurations, customer expectations, and brand standards. Upon arrival, the dealership logs the motorcycle into its system using the VIN and scans the crate's barcode to verify delivery. The crate is then moved to a prep bay, usually located in the dealership's service department. Here, technicians begin the uncrating process. The protective panels are removed with care, using power screwdrivers or pneumatic drivers to loosen structural fasteners. As the lid is lifted, the bike is revealed, still pristine, wrapped in protective films, and secured to the shipping skid. Technicians carefully release the tie-downs and wheel chocks, then roll the bike off the skid using an inclined ramp. Special attention is paid to ensure that no part of the undercarriage, fender edges, or exhaust tips contact any surface that could cause scratches. Once on level ground, the technician rolls the motorcycle to a designated pre-delivery inspection station. The PDI is a comprehensive quality validation checkpoint, essentially a dealership-level version of the factory's final inspection, but adapted for post-transit conditions. Although the motorcycle passed all functional and cosmetic checks at the factory, transit vibration, temperature changes, or handling during shipment may have caused fasteners to loosen or components to settle. The technician begins with a visual inspection, removing all remaining protective films from painted and chromed surfaces. They check for blemishes in the finish, rub marks from packaging, or contact scuffs on edges and controls. The VIN is verified against the order form to ensure model accuracy. Then, the technician proceeds to torque verification, rechecking critical bolts such as the handlebar risers, axle nuts, foot controls, and mirror stems. Any loose or under-torqued fastener is adjusted and marked with inspection paint. Next comes fluid confirmation. Although the bike left the factory with calibrated levels, dealerships are instructed to verify engine oil, primary case oil, and, if applicable, coolant levels. In some markets, fuel is added at this stage for final functional checks. In others, due to transportation or safety regulations, the tank may remain dry until final delivery to the customer. In all cases, fuel is added using clean, filtered dispensers to avoid introducing particulates into the fuel system. The technician then performs a battery check. During transport, the motorcycle's AGM or lithium-ion battery is either partially charged or disconnected. At the dealership, the battery is removed, placed on a calibrated trickle charger, and brought up to a full state of charge. Voltage is measured with a multimeter, and current draw is checked once the ignition is switched on. After installation, the technician verifies that the motorcycle boots correctly, displays no diagnostic trouble codes, and responds to all switchgear inputs. Tire pressure is another key checkpoint. Changes in altitude or temperature during shipping can cause pressure loss, so the technician inflates both tires to factory specified PSI using a digital gauge. Tread depth is verified, although these tires are brand new and usually measure well beyond the legal minimums. Once all systems are live, the motorcycle is rolled onto the dealership's diagnostic platform. This platform communicates directly with the ECU via a Harley-Davidson approved scan tool. The technician checks firmware versions, confirms that all required software updates have been applied, and clears any factory test data that may have been left from dyno runs. The diagnostic tool also performs a health check on the bike's CAN bus network, ensuring that all sensors, control modules, and devices are communicating properly. After all mechanical and digital checks have passed, the motorcycle is wheeled to the detail bay. Here, the dealership's appearance team applies finishing touches. Chrome is polished with microfiber cloths and Harley-Davidson's proprietary metal polish. Paint is cleaned with a static-free spray and buffed to a high gloss shine. Blacked out engine finishes, brushed aluminum components, and wheel spokes are all treated with appropriate surface-safe cleaners. Seats are wiped clean and conditioned if made from natural leather. If the motorcycle is a custom factory order, one tailored to a specific customer, it may receive additional dealer-installed accessories at this point. These might include windshield kits, backrests, auxiliary lights, luggage racks, upgraded exhaust, or even factory-authorized tuning modules. Each accessory is installed using torque specs and routing guides provided by Harley-Davidson's official P&A division. These installations are recorded on the customer's service profile, ensuring future support and warranty clarity. Once all final touches are complete, the motorcycle enters dealer storage or showroom staging. Dealerships take care to store motorcycles in temperature-stable environments, away from direct sunlight and excess humidity. Bikes may be placed on carpeted mats to prevent tire flat spotting during long storage periods, and some even use clear plastic dust covers to protect high-end finishes. Every day, the service staff perform quick inspections of the showroom fleet, checking for battery drain, tire sag, dust accumulation, or fluid seepage. These checks ensure that even if a bike sits for several weeks before sale, it remains in peak condition. And then comes the final moment, the handover to the rider. When a customer arrives to pick up their new Harley-Davidson, the dealer performs a last-minute walkthrough. The technician explains the startup procedure, walks through the bike's controls, answers questions about maintenance intervals, and ensures that the buyer understands any features like ABS, cruise control, ride modes, or Bluetooth integration. The owner receives their key fobs, documentation packet, warranty terms, and a printed PDI checklist signed by the technician. Some dealerships even celebrate the handoff with a ceremonial bell ring, a photograph, or a first engine start with the customer at the controls. Before the hum of torque wrenches or the hiss of pneumatic arms ever begin their synchronized dance, the production of a Freightliner truck starts much earlier at the material level. Freightliner, as a brand under Daimler Truck North America, sources its materials globally but manufactures domestically with an emphasis on high efficiency, high quality, and lean production methodologies. In practice, that means every component, from the massive frame rails to the smallest electrical connectors, follows a strict protocol from the moment they're commissioned. The backbone of every Freightliner truck is its chassis, and that begins with the steel. High-strength, low-alloy steel, engineered specifically to provide structural rigidity while reducing weight, is delivered in massive coils or long billets. These raw materials are typically sourced from certified mills across the US and Canada. Each shipment comes with metallurgical certification to ensure the proper carbon content, tensile strength, and fatigue resistance required for heavy load applications. Once the steel arrives at the plant or designated fabrication facility, it undergoes an initial inspection. Visual checks confirm the absence of surface defects like lamination or rust, while ultrasonic sensors or X-ray systems may be used for internal flaw detection. From there, the steel enters the cutting phase. Frame rails, the long backbone beams of the truck, are precision cut using CNC plasma or laser cutting systems. These machines follow CAD-generated paths to carve out the exact dimensions needed, often with tolerances down to fractions of a millimeter. Automated feeders load each steel section onto rollers, feeding them beneath gantry-style cutting heads. Sparks fly, not chaotically, but in orchestrated arcs of heat and light, as the steel begins to take its first identifiable form. But cutting is just the beginning. Each cut rail or cross member must be drilled, beveled, and punched to accommodate brackets, wiring looms, and other structural elements. These are done using robotic drill stations and multi-axis milling centers, often clustered in work cells that operate semi-autonomously. Workers oversee quality and handle any exceptions flagged by the system. It's not uncommon for a single frame component to pass through 8 or more stages of fabrication before it's ready for assembly. Meanwhile, in a different part of the facility, or sometimes an entirely different Tier 1 supplier plant, other key components begin their own parallel journeys. The cab, for instance, which forms the command center for the driver, starts its life as a series of stamped metal panels. These are formed in high-tonnage stamping presses, where flat steel sheets are fed into dies that exert upwards of 2,000 tons of pressure to form complex three-dimensional shapes. Roof panels, sidewalls, floor pans, and door skins are pressed, trimmed, and then moved into assembly cells for robotic welding. In one of the most mesmerizing stages of production, robotic arms, each about the size of a small car, move in choreographed unison, welding dozens of seams with astonishing precision. These are spot welds, placed at strategic structural points identified through finite element modeling simulations, ensuring the cab can withstand torsion, vibration, and frontal impact forces. The welding jigs are precisely machined, holding the panels in a fixed position to prevent warping and maintain dimensional accuracy. Each weld is logged, and sensors on the welding arms monitor heat, duration, and penetration in real time, ensuring every seam meets exacting standards. Once the skeleton of the cab is complete, it moves on to the paint line, though it's not quite time for color yet. First, the cab shell undergoes a rigorous cleaning and pre-treatment process to prevent corrosion and promote paint adhesion. This includes an alkaline wash to strip oils and residues, followed by a zinc phosphate bath that chemically prepares the metal. After that, the cab is electro-coated. In this process, the entire cab is submerged into a tank filled with electrically charged paint particles. A voltage is applied, causing the paint to be uniformly attracted to every surface, even inside the seams and cavities. This e-coat layer is critical. It forms a rust-resistant shell that will protect the truck for years, even in the harshest environments. While the steel skeletons are being formed and treated, the plastic and composite parts that will furnish the truck's interior and aerodynamic exterior begin their own fabrication process. Instrument panels, bumpers, fender extensions, and fairings are typically made using injection molding. Heated polymer resin is injected into steel molds under high pressure, then cooled and ejected, forming parts that are lightweight, durable, and dimensionally stable. These components are trimmed, drilled, and sometimes pre-painted before being cued for final assembly. The engine, the heart of the Freightliner, is usually sourced from Detroit Diesel, another subsidiary under the Daimler Truck umbrella. Engines such as the Detroit DD13, DD15, or DD16 are manufactured in parallel production lines, where aluminum engine blocks are cast, machined, and built up through a layered process involving crankshaft installation, piston assembly, cylinder head mounting, fuel system integration, and finally the addition of sensors, electronic control modules, and turbochargers. Each engine undergoes a hot test, where it's fired up and run under load conditions before it ever ships to the truck assembly plant. Transmissions and axles, often sourced from Eaton or Detroit Axle, are built in similar fashion, tested, and then sent in just-in-time batches to the Freightliner facility. Inventory control is tightly managed. Freightliner follows a lean manufacturing strategy, meaning parts arrive in closely timed windows based on actual production schedules. This minimizes storage needs on site and keeps the factory floor clear and efficient. By now, dozens of subsystems are in progress across multiple areas. Wire harnesses are being measured, cut, and terminated using automated cable cutting machines. Instrument clusters are assembled on dedicated benches with modular electronics, and HVAC systems are pre-tested on standalone rigs. Even the seats, often custom ordered based on customer specifications, are being upholstered, stitched, and fitted with safety sensors and air ride mechanisms. Each of these elements, whether it's a 900-pound axle or a palm-sized switch, will soon converge on a single assembly line, but that's still to come. First, all subcomponents must undergo quality control checks. Engineers and inspectors use a mix of digital calipers, laser measuring systems, and coordinate measuring machines to verify dimensions. Electrical systems are continuity tested using automated probes, while air and hydraulic systems are pressure tested for leaks. Any deviation from spec is logged in a centralized manufacturing execution system, or MES, which tracks every part from cradle to completion. The MES is the digital backbone of Freightliner's production philosophy. Every cab, frame, and engine has a digital birth certificate, a file that accumulates every test, measurement, and torque spec as it moves through the line. This level of traceability allows Freightliner to not only ensure consistent quality, but to rapidly isolate and correct defects if issues ever arise in the field. At this point, with thousands of parts flowing in from dozens of stations, the stage is set. The real magic, the assembly line itself, is about to begin. This is where human skill and machine precision merge in a seamless ballet of bolts, wires, and rivets, where every 12 minutes, a completed Freightliner truck rolls off the line, ready to shoulder the burden of logistics across a continent. But the choreography that makes that happen is anything but simple. As the curtain rises on the main assembly line, the factory enters its most synchronized and visually striking phase. The rhythm of production is guided by what's known in manufacturing as takt time, the calculated beat that determines how long each station has to complete its task. For Freightliner, depending on the model and plant configuration, A new truck might be rolling off the line every 10 to 15 minutes. But behind each of those trucks is a sequence of over 500 carefully choreographed steps involving hundreds of skilled workers and dozens of robotic assist systems. It all begins with the bare chassis rails, two long beams of hardened steel that form the skeletal spine of the truck. These rails arrive from the fabrication zone on heavy-duty conveyor systems. Before they even reach the first assembly station, they are scanned for orientation, Idaho, verified via barcode, and inspected by vision systems to ensure all required holes, cuts, and fasteners are present. Then, they're placed onto mobile build carriers, massive, gear-driven fixtures that move the entire truck frame down the line at a precise, constant pace. These carriers can rotate and tilt the frame slightly, allowing technicians ergonomic access to areas that would otherwise be difficult to reach. The first phase of assembly is focused on the undercarriage, namely installing the axles, suspension systems, crossmembers, and mounting brackets. A fully loaded Freightliner may be designed to support up to 80,000 pounds of gross vehicle weight, so the frame must be fortified to handle these loads with absolute reliability. Workers install steel cross members, bolted or riveted perpendicular between the chassis rails to enhance structural rigidity and prevent torsional twisting. Next comes the installation of the front and rear axles. Depending on the model, this could be a tandem axle configuration or a single drive axle for lighter duty vocational trucks. Each axle, pre-assembled with hub bearings, brake components, and wheel ends, is hoisted into place by overhead gantries equipped with hydraulic grippers. These assistive lifting devices are guided by technicians who carefully lower the multi-ton axle into position beneath the chassis rails. Once aligned, brackets and U-bolts are torqued down using calibrated pneumatic tools, each fitted with torque sensors to ensure fasteners meet the manufacturer's precise specifications. At the same time, the suspension system is installed. For most long-haul Freightliners, this means an air suspension setup where heavy-duty airbags, connected to leveling valves, are mounted in tandem with shock absorbers and trailing arms. These systems are designed to not only provide a smoother ride for the driver, but to protect the cargo from vibration and impact damage over long distances. Airlines are routed and clipped into place, and the system is pre-pressurized to check for leaks and integrity before moving to the next station. The steering system, too, is beginning to take form at this stage. Steering gearboxes are bolted to the frame and connected via linkages to the front axle. These components, although not yet connected to a steering wheel, are functional and mechanically aligned. Meanwhile, brake lines, often color-coded and routed through stainless steel conduits, are laid out along the chassis and secured at regular intervals. These lines will eventually connect to air reservoirs and electronic braking modules, which will manage the truck's braking system with a combination of mechanical and computer-assisted precision. As the frame grows in complexity, so too does the pace of integration. Fuel tanks are installed using insulated saddles and steel straps. These tanks, usually aluminum for weight savings, are pre-tested for leaks before arriving at the line. DEF tanks, used in modern emissions systems for diesel engines, are added alongside them. In vocational trucks like dump trucks or cement mixers, auxiliary hydraulic systems may also begin installation at this point, including reservoirs, pumps, and control valves. While this underframe activity unfolds, the cab is progressing down a parallel sub-assembly line. The painted cab shell, fully E-coated and prepped, is moving through its own series of workstations where interior components are being added. First, the wiring harnesses, pre-assembled bundles of electrical cable with color-coded insulation and printed tags, are laid into place. These harnesses control everything from the instrument cluster and lighting to the HVAC system and advanced driver assistance systems. Next, the dashboard is installed. This large composite structure comes pre-populated with electronic modules, venting ducts, and sometimes even gauge clusters, depending on the configuration. The HVAC unit, assembled separately and pre-tested in an environmental chamber, is mated behind the dash with refrigerant lines and vacuum-actuated dampers. Meanwhile, sound insulation panels are installed across the firewall and floor pan. These include layered composites of foam, mass-loaded vinyl, and aluminum shielding to reduce road and engine noise in the cab. Seats are installed next. Air ride driver seats with integrated heating, lumbar support, and, in some cases, electronic adjusters. These are bolted into pre-threaded inserts in the cab floor, and once secured, connected to wiring and air supply lines. Overhead control panels, sun visors, storage compartments, and sleeper modules begin assembly as the cab continues moving. Even interior trim pieces, such as door panels, kick plates, and A-pillar covers are clipped into place at this point. Every screw, every clip, every surface must pass tactile and visual inspection by quality technicians trained to detect the slightest deviation. With the cab interior nearly complete and systems verified for fit and function, it's now ready for what's known as the cab-to-chassis marriage. This is one of the most complex and dramatic moments in the entire production sequence. The cab, hoisted on a precision gantry crane, is slowly lowered onto the rolling chassis. But this isn't a blind placement. Alignment pins, laser positioning sensors, and human guides all play a role in ensuring the cab lines up perfectly with mounting points, firewall openings, and wiring pass-throughs. As the cab settles onto its mounts, typically a mix of rigid and elastomeric bushings to absorb vibration, technicians bolt it down using automated torque tools. Simultaneously, they connect the main electrical interface harnesses between the cab and chassis. These waterproof, high pin count connectors handle everything from turned signals and headlamps to engine controls and CAN bus data networks. Airlines for the braking and suspension systems are also routed from the chassis bulkhead into the cab via quick connect fittings. The steering column is connected to the steering gear via a collapsible intermediate shaft, and the parking brake cable is attached to its actuator. At this point, the truck is now beginning to resemble its final form. The integration of cab and chassis transforms a scattered system of components into a singular, rolling vehicle platform. And with this critical milestone complete, the truck moves into the fluid fill and powertrain test zones. But before that, another major piece must be installed: the engine and transmission assembly. Unlike consumer vehicles, where engines are often installed early in the process, Freightliner trucks receive their fully dressed engines after the chassis is partially assembled. The engine transmission module arrives as a single unit mounted on a subframe, complete with turbochargers, accessory drives, exhaust manifolds, and cooling modules already attached. This assembly is lifted into place using robotic hoists, aligning with the engine cradle on the chassis. Mounting bolts are inserted and torqued down in a specific sequence to prevent frame distortion. The drive shaft, a multi-section tube with U-joints and center bearings, is connected between the transmission output and rear axle input flange. Electrical connectors, fuel lines, coolant hoses, and air intake ducts are routed and secured. From this point forward, the truck is now considered live. It contains its engine, electrical backbone, braking systems, and operational suspension, but it's far from ready to drive. A battery module installed in steel trays along the side or rear of the frame is connected and charged. Now, the vehicle can begin low-voltage diagnostics and internal system checks. The cooling module, radiator, intercooler, fan shroud, and transmission cooler is installed as a pre-assembled front-end module. This module is bolted to the front of the frame and connected to the engine via hoses and mounting brackets. Charge air ducting for turbocharged models is secured using high-pressure clamps. The HVAC condenser is integrated into this module as well, bringing together thermal management for both engine and cab. Now, with all major modules mounted and cab systems connected, the vehicle enters the fluid fill station. Here, automated filling systems inject precisely measured amounts of engine oil, coolant, transmission fluid, brake fluid, and power steering fluid. Each system is pressurized and monitored for leaks. Sensors detect flow rate, air bubbles, and fill level in real time. If any irregularity occurs, the process halts automatically, and a technician is dispatched to correct the issue before moving on. Now that the Freightliner truck has its full frame, drivetrain, cab, cooling system, fuel and air systems, and operational electrical circuits, it enters one of the most sophisticated and diagnostically intensive areas of the entire plant, the calibration and alignment zones. Here, machines begin to speak to machines, and software begins to take control. The first step is a power-on diagnostic. With the battery system now live and the truck's electrical backbone fully connected, technicians initiate the onboard computer systems. This includes the engine control module, transmission controller, ABS module, airbag control unit, body control module, and telematics gateway, among others. At this moment, the truck boots up, like powering on a small data center on wheels. A handheld or overhead diagnostic interface is connected to the vehicle's onboard diagnostic port. This interface communicates with the entire network of controllers using protocols like SAE J1939 and KN bus. The technician initiates an automated diagnostic sequence that verifies communication with all electronic modules. If any controller fails to respond or reports a fault code, the process halts, and the vehicle is flagged for further investigation in a rework bay. Otherwise, it proceeds to electronic calibration. Calibration is a critical process that sets each truck's electronics to match its unique configuration. No two trucks rolling off the line are exactly alike. One may be a day cab designed for regional haulage, while another might be a sleeper cab configured for coast-to-coast operations with collision mitigation systems and adaptive cruise control. The calibration process loads the correct firmware and parameter sets into each module, ensuring that systems like automatic transmissions shift appropriately for axle ratios, or that driver assistance systems are aware of wheelbase length and sensor positions. This is done via secure upload stations, where each truck is assigned a digital build sheet linked to its VIN. The calibration software retrieves this data from the central MES system and programs each controller accordingly. The parameters include everything from fan clutch engagement temperatures to PTO behavior and idle shutdown timers. Once complete, each module reports back its configuration status, and the entire vehicle is now digitally aligned to its physical build. Next, the vehicle moves into the alignment station. Heavy-duty laser alignment systems, mounted on rails or fixed towers, are used to measure the orientation of the front steering geometry and rear axles. Unlike passenger vehicles, trucks often have multiple axles that must be precisely aligned, not just for handling, but for fuel economy and tire wear. Toe, camber, and thrust angles are all checked in real time. Technicians use alignment racks, where the truck is driven or pushed onto a set of turntables and sensors. The wheels are clamped with reflective targets or optical sensors, and the alignment rig projects laser beams to calculate angles down to fractions of a degree. Adjustments are made on the spot, typically by rotating tie rods or adjusting shims, until all values fall within Freightliner's tight specifications. With alignment complete, attention turns to tire and wheel torque verification. Even though wheel and tire assemblies were installed earlier, every lug nut is now checked using either digital torque wrenches or wheel torque verification robots. These tools not only confirm that each nut is tightened to specification, but they record the actual torque value in the MES system, tying it permanently to that truck's build history. Any deviations are logged, and the operator must reperform the torque sequence until it passes. The vehicle now proceeds to what is perhaps one of the most dramatic stations in the entire factory, the rolling test bay. These bays simulate real-world road conditions using massive rollers embedded in the floor. The truck is driven or guided onto the rollers and secured in place using heavy chocks and hydraulic clamps. The goal is to test engine performance, transmission shifting, braking behavior, and electronic stability systems in a controlled environment. A technician enters the cab and starts the engine. Diagnostic software monitors over 1,000 real-time data points while the truck is run through a series of controlled cycles. The accelerator is gradually pressed, spinning the drive wheels up to simulated road speeds. The automatic transmission is monitored to ensure proper gear changes. The ABS is triggered under simulated braking, verifying sensor input and control module logic. While the truck is driving in place, exhaust gases are routed through a ceiling-mounted emissions probe. This system continuously analyzes the output for nitrogen oxides, carbon monoxide, hydrocarbons, and particulate matter. The truck's aftertreatment system, which includes diesel oxidation catalysts, diesel particulate filters, and selective catalytic reduction modules, is monitored to confirm that emissions stay well below EPA and CARB limits. At the same time, the system also confirms that the engine software is not modified, tampered with, or otherwise non-compliant. This is done using secure electronic handshake protocols between the ECM and the test equipment. Once the rolling test is complete and all values fall within acceptable limits, the vehicle proceeds to the leak and pressure test station. This station tests all air systems for integrity, including air brakes, air suspension, and air horn systems. The truck is parked, and the air tanks are fully pressurized using either the onboard compressor or an external air source. Sensors monitor the system for pressure decay, typically looking for less than a 2 psi drop over a fixed time window. If the system passes, it is deemed leak-free. If it fails, it is routed to a diagnostic bay for smoke testing or manual inspection. Similarly, the HVAC system is tested for refrigerant charge and performance. A technician activates the air conditioning and heating functions while monitoring the vent outlet temperatures. This ensures that the climate system is operating within spec before the truck is shipped. Even the windshield washer system is activated, and fluid reservoirs are topped off as needed. Now, nearing the final phase of the build, the truck enters the fit and finish inspection zone. Here, the human eye and hand still reign supreme. While automation excels at measuring torque and electrical signals, it takes trained inspectors to detect cosmetic defects, misaligned trim, or imperfect panel gaps. Workers walk around each truck with checklists in hand, inspecting everything from door seals and mirror mounts to paint finish and decal placement. The doors are opened and closed to check for proper latching. The cab lights, headlights, turn signals, brake lights, and reverse lights are all tested. The horn is honked, the wipers are activated, and the radio is briefly turned on to verify speaker operation. For trucks with sleeper cabs, technicians crawl into the bunk area and test interior lighting, power outlets, and optional features like inverters or bunk HVAC units. If the truck passes all these visual and functional checks, it's moved into the detailing area. Here, protective films applied earlier in the assembly process are removed. The cab and chassis are wiped down to remove any assembly dust or handprints. Paint is polished if necessary, and tire shine may be applied for customer delivery presentation. As the truck sits, gleaming under overhead lights, it's finally ready for what's called a road-ready release. A final supervisor, often with years of experience, performs one last walk-around, signing off on the truck's build sheet. This triggers the MES system to mark the unit as complete, at which point a unique certificate of conformance is generated. This document certifies that the truck meets all Freightliner build standards, federal safety regulations, and emissions compliance requirements.